Good afternoon and welcome to the FlyZero webinar, A Vision for the Future of Zero Carbon Emission Air Travel. I'm Sophie Lane, the Chief Relationships Officer with ATI, and I'm going to guide you through what promises to be a really interesting event. For those of you who are not familiar with FlyZero, the project began in early 2021 as a study into the feasibility of zero carbon aircraft. FlyZero is a project that is led by the ATI, but it is funded by the Department for Business, Energy and Industrial Strategy. And as an independent study, FlyZero brought together a number of experts across the UK to assess the design challenges, manufacturing demands, operational requirements, and the market opportunity of potential zero carbon emission concept aircraft. Today, hopefully you've seen that we've published the flagship report, and that shows a revolutionary vision for a new generation of aircraft powered by liquid hydrogen, keeping businesses, cultures, families, nations connected without the carbon footprint. Today, you're going to hear from the team behind the project on their findings and recommendations, and hopefully engage in an enjoyable discussion to really delve into how they came up with those conclusions. Today's event is going to be run in 3 parts, and we're going to have a short break between each one. During the event, you're going to have the opportunity to ask questions. There is a QR code that you can follow, or please head to slido.com and use the code 547152 if you want to ask a question. We are recording today's event as well. And first up, I'd like to introduce Paul Griffiths. He's the head of the aerospace team at BAYS.
Great. Thank you, Sophie. It's good to see you all this afternoon. I'm really pleased to be able to stay and to hear from so many excellent speakers. I've been watching the FlyZero project closely. It's been making really rapid progress, and the publication of its findings this week is hugely exciting. Before saying any more, I'd first like to give my congratulations and thanks to Chris Gear and his team on the excellent work that they've done. And I want to talk to you about why the Department for Business, Energy and Industrial Strategy funded the FlyZero study, and recognise the contributors to it and explain how it supports our broader decarbonisation agenda. So first, why did BAYS fund the FlyZero study? The project has been a change in our recent approach to aerospace technology, but the evidence is increasingly clear. The UK and the global community face a huge and urgent challenge in reaching net zero emissions in order to avoid the worst effects of climate change. Decarbonising aviation is one of the biggest challenges on our journey to net zero. It will require new technologies and significant new investments. Beyond that, we must address the long cycles in aviation, develop new regulation and build international cooperation. To accelerate progress, the government is bringing stakeholders together through the creation of the Jet Zero Council, and we've outlined our overall framework for achieving net zero aviation by 2050 in DFT's Jet Zero consultation. About 18 months ago, we saw that there was a huge unknowns and much ambiguity around what was technically and commercially possible. It was not clear what route the UK could take when it comes to zero carbon emission commercial flight. FlyZero was therefore born out of a need to understand better what could be possible and how the UK could put itself in the best position to achieve this. It was created to help drive across the UK and internationally a consensus on how to achieve zero carbon emissions commercial flight. Other countries were also wrestling with these issues, but none has approached this problem in the same sort of novel and collaborative way as FlyZero. The project was deliberately set a big challenge and a short period of time to mobilise and find answers. While there's still a huge amount of work to be done, I'm delighted with the results that it has achieved so far. I want to talk about the contributions to the project, acknowledge these and also reflect on the capability that this is showcased in the UK. We know that several UK companies are working on ambitious proposals for zero emissions propulsion in aircraft, but to fully address the emissions challenge and get the most economic benefits for the UK, we also wanted to encourage wider collaboration across the sector, and that's exactly what's happened. The vast knowledge base we have in the UK across industry and academia has been showcased in the work that FlyZero has undertaken. With 13 contributing companies, 16 research institutions, and additional work packages with industry, this has been a massive collaborative undertaking, and I'm also grateful to the UK Aerospace Research Consortium for the work that it has done to coordinate efforts between universities and industry. And I'm really interested in hearing more about the new ways of working that have been developed and how a new high-performing team was established virtually amidst the pressures of COVID-19. It's been an incredibly impressive performance, and really interesting to see how industry can, when needed, come together just as it did in the ventilator challenge to address an urgent problem. So let me explain how FlyZero contributes to a wider and ambitious programme to decarbonise aviation, and how the findings from FlyZero will help to inform future aerospace activity. FlyZero has now set the foundations for further cross-industry work on achieving zero-emissions flight. We have eagerly awaited its findings and recommendations, and we're going to carefully read them and consider them in developing our future clean growth and aviation technology strategies and activity. And this is going to be done alongside industry and academia. The government is committed to supporting the aerospace and aviation sectors as we transition to net zero, and the recent spending review demonstrates this, extending the government support for the ATI programme to 2031, alongside around 200 million of funding for sustainable aviation fuel and infrastructure research and development. My team will now turn to working with the ATI, Innovate UK, industry and research organisations to establish priorities for the ATI programme going forwards. We will support a ramp-up of new research activity that will in turn lead to cleaner growth and economic benefits around the UK. So finally, what comes next? Again, a big thank you to the FlyZero team and everyone who's contributed to the project. It's great to see the ATI inspiring such new ways of working. Now is the time to build on the work of FlyZero. We want to expand and build the UK's capability to ensure we are a leader in the zero-carbon commercial aircraft of the future. UK businesses are well placed to take advantage of the new global market that the transition to clean aviation will create. There will be opportunities for established firms to grow more, SMEs to serve new customers, and innovation will drive the creation of new startups. FlyZero is publishing a huge amount of detail on its findings. I hope this inspires you all to consider new research topics and commercial opportunities. The webinar today is going to be fascinating, and I wish you all success and look forward to hear more from you. Thank you, and I'm going to hand back to Sophie now.
Thank you, Paul. Really appreciate the time that you spent with us today. And thanks again to Bays for all of the support that you've shown throughout the FlyZero project. So next up, we're going to hear our presentations from the FlyZero leadership team on their key findings. And you're going to see some videos from David Debney, Simon Webb, and Chris Pickard.
Good afternoon, everybody. My name's Dave Debney. I'm the Chief Engineer for Whole Aircraft Integration on FlyZero. This afternoon, I'm going to introduce you to our 3 zero-carbon aircraft concepts. But first, I'd like to cover a bit of the background and the context as to why it was important for FlyZero to produce these concepts. These concepts are to demonstrate the potential of zero-carbon flight. They're not intended for production. The ATI is not an airframer and has no intention of becoming one. It's really about exploring the challenges and opportunities of integrating the technology. You can look at technology at a component level or system level, but until you wrap it up to an aircraft, it's very difficult to assess it against other aircraft products. And that was one of the key reasons why this was important. In addition, until you really look at integrating those systems together, there are many aspects of the problem that you won't uncover, and that was a key part of what we wanted to look at on FlyZero. The aircraft modelling that we've done on FlyZero was built on the foundation of aircraft modelling capability that existed in the ATI, as well as some of the expertise that's come in from the secondees and the fixed-term contractors that have been working in the team. We're working closely with the ATI to ensure that the models and the capability developed within FlyZero to look at zero-carbon architectures will be fed back into the ATI to be used for the benefit of the UK in future. The aircraft concepts form the basis of the market analysis and then subsequently the sustainability assessment to get a total picture of the impact of what these concepts could achieve. And that's something that the ATR will be looking to build on in the future. In addition to the three concepts, we've also created three baseline aircraft. These use SAF as a fuel and are intended as a basis for comparison with the same technology level and the same mission, so that we can get as close as we can to an apples to apples comparison of hydrogen against SAF. And we'll come back to that when we look at the concepts. First of all, I'd like to look at where we started in this process. At the start of FlyZero, we looked at all the different zero carbon technologies, not just liquid hydrogen, so things like ammonia and batteries as well. And we needed to make sure that the team had the freedom to innovate and really come up with something that could push the envelope and potentially make us look at the problem in a different way. So we created a series of scouts, and we've shown various ones in the diagram here. We looked at many different options, including blending wing bodies, separate fuselage for fuel storage, box wings, different fuselage shapes, joined tails, battery electric distributed propulsion, 27 different aircraft configurations in all. We then used a comprehensive scoring system to narrow down to the final three concepts. The first of these concepts is the regional concept. This carries 75 people up to 800 nautical miles. There are some key technologies here, and the objective of this concept was to demonstrate the feasibility of a fuel cell aircraft. The fuel cell system is located in the belly of the aircraft. You can see the units in the picture on the screen. It's a fuel cell electric system, which means the fuel cell is then connected to electric motors to drive 6 propellers on this concept. Going electric gives you the ability to have multiple propulsors, which is something that needs further work, but we felt it was important to illustrate. This aircraft concept has vacuum insulated hydrogen tanks, 2 of them in the rear of the fuselage. One of the key integration challenges for this fuel cell aircraft was heat management. We have heat exchangers in the nacelles, and they are working hard to reject all the heat produced by the fuel cell system. At the moment, at this size of aircraft, we're using our 2026 TRL6 technology assumptions. This aircraft ends up using slightly more energy than an equivalent SAF-powered aircraft. The conclusion that we've drawn from that is that with that technology level, this aircraft is the largest size that you would want to go to with a fuel cell. And if you were to make the aircraft smaller, the fuel cell would likely become more competitive. As technology improves, the fuel cell capability in terms of aircraft size will increase. Next, I'd like to introduce the narrow-body concept. The key objective of this concept was to look at whether hydrogen could be competitive in the size class that is the workhorse of commercial aviation. So this, you'll see that we've matched closely the capability of an A320 or 737 with 180 single-class passengers and a design range at full payload of about 2,400 nautical miles, which is very similar to both the A320 and the 737. In terms of the technologies on this aircraft, we've introduced a few different things. The first is that we've created a very compact layout for the hydrogen system. So the hydrogen tanks, the turbofans to provide the propulsion, and the entire fuel system are all located in the rear of the aircraft. That does give us some challenges around managing the center of gravity and specifically the shift during flight. So we've gone to a 3-surface control configuration. So you can see the canard, the tail, and the wing, the 3 surfaces. We've also introduced what we're calling a laminar flow fuselage on this aircraft. The idea is that using varying cross-section, it's an opportunity to reduce the fuselage drag. This also has the benefit that it produces a larger diameter at the rear of the aircraft, which is ideal for increasing the efficiency of the hydrogen storage. If we look at the mission comparison for this concept, the fuel mass is significantly lighter, as we would expect, but actually from an energy perspective, the narrow-body concept uses less energy than an equivalent technology SAF-powered aircraft. And finally, the mid-size concept. So this aircraft is designed to address long-haul flying with zero carbon. This aircraft is designed to go from London to Auckland in New Zealand with 2 hops and 1 stop. This is a game changer for zero carbon aviation. This is something that until recently was generally assumed not to be possible, but the FlyZero analysis suggests that it is indeed feasible. This aircraft has a large hydrogen tank at the rear and 2 delta hydrogen tanks in front of the wing. It uses turbofan propulsion, and the hydrogen is then used to power those turbofans and fed through the aircraft. Again, the fuel mass for the mission comparison is significantly lighter than the baseline, and this aircraft again uses less energy than the baseline would do. We feel that this is a really important conclusion from the FlyZero project, that hydrogen is not just capable of solving a problem in terms of short haul and small aircraft. Hydrogen could potentially be expanded to cover a significant portion of flights. So in terms of the conclusions, what have we learned from this concept activity? Well, as I said earlier, the concepts are 3 possible solutions that the FlyZero project has come up with. The hydrogen storage dominates the choice of architecture. Where do you put various systems? You start with the hydrogen storage because of the volume challenge that's associated with hydrogen. We've discovered that flight operations with hydrogen are fundamentally different. The shape of the payload range diagram, the ability to trade fuel for range, which is a given on kerosene aircraft and something we're all used to, doesn't exist in the same way. The concepts are based on the FlyZero technology projections, and we should note that they are therefore sensitive to changes in things like the efficiency of the hydrogen storage. Safety is another critical consideration. We've designed these concepts using FlyZero design principles which were derived by the project. Things like we have to keep the hydrogen storage outside of the uncontained engine rotor failure zones. Currently, the hydrogen regulations don't exist that would be needed to bring one of these aircraft into service. Global cooperation is going to be needed on this. This represents an excellent opportunity for the UK CAA to re-establish itself as a global player in the regulation space. There are many challenges to characterise and solve before these hydrogen aircraft could be brought into service, and this is one of the key topics that will be covered in the Technology Bricks presentation later this afternoon. However, the concept work that FlyZero has done has certainly shown sufficient promise that hydrogen research should be continued in parallel with SAF. I really think that these concepts, particularly the mid-size, represent some new thinking on zero carbon aircraft and represent the future, a possible future for zero carbon air travel. Thank you very much.
Hello, I'm Simon Webb and I'm the Chief Engineer for Propulsion on FlyZero, and I'm going to give you an overview of the technology options and challenges we've been working on over the last year. So firstly, as I explained in the last webinar, and as we've now documented in our zero carbon fuel comparison paper, we've down selected to liquid hydrogen as the preferred fuel for zero carbon flight. The main driver here is that as well as producing our CO2, hydrogen is very light. It's around 3 times more energy dense than kerosene, which is a key dominating factor for aerospace. However, when it's a gas, it's very large. It has low volumetric density. This does improve when it's liquefied. However, this presents a key first challenge in that hydrogen is only liquid at very low temperatures, at around minus 253 Celsius or 20 Kelvin. So significant work is needed to create a cryogenic tank and fuel delivery system to be able to make this viable for aerospace. Hydrogen is also a very small and energetic substance, so there's additional challenges around sealing at joints, leakage, and potential permeation over time into materials. These are the 6 technology bricks we've identified as being fundamental in order to realise liquid hydrogen fueled flight in the future. And we've also identified these 7 cross-cutting factors to look at, and these will be critical in ensuring that a future hydrogen aircraft could be commercially attractive and operationally viable, and allow us to understand the overall sustainability picture across the life cycle of an aircraft. A technology roadmap has now been generated for each of these, and we have positioning papers to cover all the cross-cutting challenges. We put these technologies into our FlyZero concepts, as was talked about earlier, and have been considering what would need to happen in order to make these viable in the future. On aerodynamic structures, there's a continued need to look at increasing the efficiency whilst reducing the mass of these structures. For example, in developing efficient, lightweight dry wings, as the cryogenic fuel will no longer be stored in the wings. The fuel will be stored in the fuselage, as these tanks need to be large and ideally as close to spherical as is practical in order to keep them lightweight from a structural and thermal sizing point of view. Also, making these tanks from composites in the future could offer a significant advantage, so we think this is an area to look into and develop further. There are significant new challenges with a cryogenic fuel delivery system. We've looked at knowledge from other industries, such as the space industry, but there are many different requirements for aerospace, particularly around the conditions that the fuel would be stored at, the requirements through life, the manufacturing rate and life cycle cost that aerospace requirements present. Gas turbine technology looks attractive, and so we're advocating investment in this area in the future, particularly around the combustion system and the development of a fuel delivery system with heat exchangers within the gas turbine. Our studies show that it would be viable to make a hydrogen gas turbine more efficient and produce less NOx than with other fuels. Thermal management and heat exchanger technologies will prove important as well for a hydrogen-fueled aircraft, as there's a need to add significant heat to the cryogenic fuel before it enters the gas turbine combustion system. And there's a significant challenge dealing with the heat rejection from proton exchange membrane fuel cells that we've selected. This could be exacerbated by the fact that current low temperature fuel cells produce heat at a relatively low temperature, and this can result in a relatively small temperature difference to atmosphere, particularly in hot environments and on takeoff on the ground, which is proven to be the sizing case for a fuel cell system. However, there are opportunities to be explored in the longer term, such as investigating the potential development of higher temperature PEM fuel cells to look to reduce the mass and drag of such a thermal system. Also, if we did develop this technology, there's potential to exploit that across multiple sectors. Also, there's the rest of the power electronics system for an electrical powertrain, including looking at high voltages at altitude, the challenges that go with that at high altitude and low pressures, and developing the efficiency of electrical units and electrical machines. So I talked about what would be needed to introduce liquid hydrogen fueled flight. This, however, would clearly require a new clean sheet aircraft design and significant investment in the ground infrastructure to go alongside that. So we're advocating multiple routes to decarbonise aviation in the future. So including liquid hydrogen, but also continuing to look at the production and use of sustainable aviation fuels from existing feedstocks, biofeedstocks, waste feedstocks of greases, oils in the future. But looking long term at the scalable solution of power to liquid SAF. So using hydrogen and CO2 extracted out of the atmosphere, going through a Fischer-Tropsch process to produce that fuel with increasing blends with kerosene. This would require investment in the today relatively immature direct air capture of CO2 from the atmosphere, and that would need to be scaled up and made economic. We need to continue to invest in improving aircraft efficiency, both in terms of making it lightweight and the fuel efficiency of future aircraft. As across different fuel options, kerosene, SAF and hydrogen, for different reasons, we think there's a significant risk. The cost of producing these fuels and the price of these fuels ultimately will increase in the future. We also think there's a place for improving flight path management in terms of making flights efficient, minimizing waiting times, etc. But also from a sustainability point of view, progressing the technology in weather path predictions, and so minimizing the time over which flights would travel through supersaturated regions where persistent contrails are at a higher risk of being formed. So looking forward at where green fuels could help decarbonise aviation across time and across the different capability spaces, there's definitely a place for sustainable aviation fuels, and that will be needed for the existing fleet with increasing blends going forward. But alongside that, we believe there's a space for electric battery powered flight at the shorter, smaller range aircraft, and then going up to, in the medium term, gaseous hydrogen fueled flight, and then building up to long term as you need to go further and will want to have larger aircraft flying with green fuels, moving towards liquid hydrogen. This will, however, require significant investment in onboard technology and in ground-based infrastructure in producing the fuel and around airports. If early flights happen with gaseous hydrogen, we think that would be a great starter in terms of starting the conversation with airports around handling hydrogen as a fuel, and with the authorities around the suitability of regulations and certification criteria and acceptable means of compliance, and driving that conversation forward for the long-term move towards liquid hydrogen as a fuel. And as a new fleet is introduced, we think strategically liquid hydrogen will be the best option for the vast majority of the aircraft sectors. Fuel costs will drive it that way, and the need to have an improving aircraft capability. So overall, we think there's a place for power to liquid SAF and liquid hydrogen, and that these together can address the vast majority of the market, and that liquid hydrogen as a fuel has the potential to be energy efficient and a relatively economic fuel. So if you'd like to know more now, the ATI website with the FlyZero reports is now live. Feel free to go and look at these technology roadmaps, the cross-cutting papers, and all of these other reports that are now going live on the website. Here's an example of one of the technology roadmaps to show you how these will look and feel, and what level of detail would go into these. We'll have several of these roadmaps throughout these reports, and the target here is to drive action to have technology ready to be committed into a new aircraft in 2025, to take that forward and be developed through a development program ready to go into service in the 2030s. So to summarise, green liquid hydrogen presents a pathway to decarbonise aviation. We believe it's a preferred fuel for aerospace because it's relatively energy dense, and this is important. Energy efficient, it's relatively energy efficient to produce, so this makes it economic, and will also reduce the carbon footprint of the full value chain of producing the fuel and using the fuel on board, and so minimise the demand in the green power generation network in the future. This presents a step change for technology in terms of development of and maturing these new technologies. So significant investment and action is needed. In FlyZero, we've assessed and studied the technology challenges here. We've seen no hard blockers, but we recognise substantial investment and action throughout industry, and the research network is required to make this real. And that the UK needs to accelerate to keep pace with what's happening around the globe, and needs to collaborate. No one country, no one company can do this on their own. So we need to work together for the good of the industry and the planet. FlyZero is now publishing our technology roadmaps and reports. So if you'd like to know more, go on the ATI website, look at those roadmaps, look at those reports. Also, if you're particularly interested in the technology, then look out on the 22nd and 23rd of March for these technology talks. Please register, sign up and join these sessions to learn more. And one last thing on a personal note, I'd like to say I've really enjoyed working on this program. One, because of how interesting the challenge and the technology is, but also because of how we've worked and the fantastic team we've had around us on this program, but also that we've had over 60 organisations who've participated and contributed. So I'd like to say a huge thanks to everyone who's been involved.
Hi, and thanks for joining us today. I'm Chris Pickard, and I'm the Airport Operations and Requirements Specialist for FlyZero. Along with my colleagues Helen Ledbetter and Anna Post-McCallance, we've been focusing on what impact hydrogen aircraft will have on airports, airlines, and airspace. In particular, we've looked at the hydrogen journey as shown on this slide, focusing on the production of green hydrogen, its transportation, liquefaction, on-airport distribution, aircraft refueling, and then onto the effect of hydrogen aircraft on the airspace operations. So we identified and assessed three main pathways for hydrogen supply to airports and aircraft. In scenario 1, hydrogen is generated off-site, most likely close to sources of renewable energy and other industrial hydrogen users. Hydrogen is also liquefied off-site before being transported to the airport in tankers as liquid hydrogen and then stored on site at the airport. In the second scenario, hydrogen is still generated off-site in similar locations to scenario 1. However, instead of being transported as a liquid in tankers, it's delivered as a gas via a pipeline. Once on the airport, the gaseous hydrogen is liquefied on site. And finally, in the third scenario, both electrolysis and liquefaction are carried out on the airport, with the airport only needing to be supplied with electricity and water to generate the hydrogen. So as we start to look at these in more detail, through undertaking case studies at UK airports, we've evaluated which scenarios would be the most appropriate for airports of varying sizes. In the early years of hydrogen adoption, most airports would be likely to adopt tanker deliveries, as shown in now scenario 1, as this requires the least capital investment and is relatively easy to scale as the demand grows. However, as the demand grows further, particularly at large airports, the logistics of tanker deliveries could become a challenge. For example, at large airports, our studies have shown that by 2050, nearly 500 tanker deliveries a day could be needed. At these levels, we expect scenario 2 to become far more attractive, requiring a gaseous hydrogen pipeline and on-site liquefaction. Although this requires significant energy, in the context of the overall energy transformation required by 2050, this may be achievable. However, with the exception of very small airports with low demand but plenty of renewable energy, we're not expecting scenario 3 with its on-site electrolysis to be a preferred option. For example, for a large hub airport, our studies showed that electrical demands could be well over 4 gigawatts by the year 2050. So as well as the supply to the airport, we also evaluated the on-airport distribution of liquid hydrogen to the aircraft. Similarly to the supply of hydrogen to the airport, we expect that refueling using mobile bowsers will be the most likely solution at low demand levels and for small airports on an ongoing basis. Although similar to existing bowser refueling using kerosene, The operation would, however, be more challenging due to the requirements of maintaining the cryogenic temperatures. As demand levels increase, airports may need to consider hydrogen refuelling systems to avoid an unmanageable bowser operation. Like the supply to the airport, the need to move away from tankers and bowsers may come sooner for hydrogen operations due to the increased volume of liquid hydrogen required when compared with kerosene. The hydrant system may be similar in layout to a conventional fuel hydrant system. However, to keep hydrogen as a liquid will require cryogenic pipelines and a far more complex overall system, potentially including liquid hydrogen transfer tanks located on or underneath the apron stands. So after looking at the supply of hydrogen to the aircraft, we then also investigated the potential impact of hydrogen refuelling on the speed of the aircraft turnaround at the airport. For airlines, the fast turnaround of aircraft is essential to achieve high utilisation and a commercially viable schedule. To maintain very fast turnarounds, often refuelling takes place simultaneously with other aircraft servicing activities. However, due to the uncertainty of refuelling with liquid hydrogen, there's a possibility that no other activities can take place while refuelling is also being carried out. The chart on this slide shows, for each of the FlyZero concept aircraft, how the turnaround times will compare with turnaround times for similar current aircraft. For each concept aircraft type, shown in a different colour, the column to the left of each shows how long a turnaround could take if no simultaneous activities are allowed during refuelling. In each case, you can see that this exceeds the current minimum turnaround times, which are reflected by the grey bar. The second column for each aircraft shows that if some activities do take place simultaneously, the turnaround is close to that of the existing aircraft, albeit still slightly longer. The final column for each aircraft shows that with the simultaneous refuelling, it may be possible to match current turnaround times. So using the narrow-body aircraft as an example in the green, with no simultaneous activities, in this scenario, which is based on a set hose size and refuelling velocity, the estimated minimum turnaround time is shown as 46 minutes. If some simultaneous activities are allowed, this is reduced to 35 minutes. And when there's no restriction, then the minimum turnaround time could be reduced to 27 minutes. The reason for this concern over whether simultaneous activities can take place is due to the potential for much larger refuelling safety zones. Current refuelling with kerosene requires a 3-metre safety zone, which allows for most other activities to take place at the same time, whereas with hydrogen refuelling, this safety zone could be much larger. However, studies for FlyZero by the HSE have indicated that while a 20-metre safety zone may be required during connection and disconnection of fuel hoses, it might also be possible to reduce this zone to 8 metres during the refuelling process. This would allow some simultaneous activities to take place. To further reduce the impact of the increased safety zone, it's also anticipated that some of the turnaround activities would need to be automated to reduce the risk to individuals. In addition, refuelling hoses for hydrogen are likely to be larger and heavier due to their insulation materials. Therefore, some level of automation of the refuelling process may also be required. But subject to further analysis, through process changes and automation, we think that the overall turnaround time may remain broadly similar to the current process. As well as the aircraft's operation on the ground, FlyZero has also investigated air traffic management operations to understand the ability of ATM to support and enable zero carbon emission aircraft. An important finding from the project so far has been that the current FlyZero concepts have similar airspace requirements to existing aircraft and don't display any attributes preventing them from integrating within the ATM system. However, regardless of hydrogen aircraft, changes are needed in how airspace operates. Without changes to airspace, the current system will be unlikely to cope with the forecasted traffic volumes in the coming decades. Therefore, the current ATM system needs to undergo improvements to enable efficient flight operations to continue as demand increases. There are various solutions proposed to introduce technological and operational changes. By 2050, these improvements are estimated to improve flight efficiency and reduce CO2 emissions by 6 to 10%. But importantly, focusing on the hydrogen aircraft, these same changes will reduce the requirement for liquid hydrogen and the corresponding energy to produce. To help improve flight efficiency, and therefore to reduce the demand for fuel and eventually hydrogen, typical measures and initiatives include optimizing flight paths in free route airspace, optimize processes such as collaborative decision making between airspace managers, airport operators and airlines, and optimize technologies and concepts such as high resolution weather data for headwind and contrail avoidance and formation flying. While each initiative alone may have a small impact, the sum of these marginal gains can provide much more significant benefits overall. Understanding the sum of these gains provided by ATM and facilitating their implementation will be an important step towards shaping more efficient airspace and making it ready for new future hydrogen aircraft. Although these slides have only given a very brief introduction to some of our work for FlyZero, more information is included in our report, Hydrogen Infrastructure and Operations, which is available on the ATI website. So thanks again for joining us today, and we really hope you'll find the summary report interesting and useful for the future.
Thank you for joining us again. So hopefully you enjoyed those videos. I felt they were really comprehensive, although I noticed that Chris described them as a brief introduction. So I'm sure you will find a lot more information in the reports. So we're going to move to a panel discussion now. And as you can see, Dave can't actually join us today. And so we've been joined by Mark Willier, who's the Chief Engineer for Airframe, and Simon Webb and Chris Pickard, who you have already heard from. So I'm just going to open up and start by asking, what was the driver behind developing the three concepts?
Okay, Sophie, if I can take that one. I guess there are a number of drivers, so I'll try and talk you through them as briefly as I possibly can. I guess firstly for us, we wanted to look at a range of aircraft that would maximise our impact on CO2 release, and therefore so we could look to optimise and maximise what reduction we could make in the future. Closely linked to that was the need to look to get coverage over existing routes, just to give us the best possible chance of commercial exploitation. The concepts were also selected to enable us to explore both technologies and the integrations of technologies onto various types of airframes. And each one of the individual concepts, as Dave described earlier, did provide specific challenges to that end. Also, finally, we needed to understand what capability we would need to look to exploit a zero carbon aerospace and aviation future. So I guess in a nutshell, that would cover why we looked at the three concepts.
Okay, thank you. And I mean, in talking about those concepts, and Simon, you touched on this a bit, there are a huge number of technologies that are going to be required to be developed further in order to make the timescales that you were talking about. How feasible do you think that is?
Well, firstly, I think there's a real imperative to move quickly on developing these technologies. If we're going to contribute in aviation to fulfilling some of the Paris Agreement commitments, then secondly, I do believe that the targets we've set ourselves that are laid out in these technology roadmaps are feasible. That's not to say that they would be easy to achieve. There's many different technologies and many different challenges around those technologies, some of which we don't fully understand yet, but we've laid out based on the conceptual study work we've done in those roadmaps. So I think immediate action and investment is required if we are to try and meet those timescales and those targets. It's very encouraging for me and the whole team to start to see a number of companies are now moving as well. We've seen a real acceleration in action around hydrogen and the technologies that underpin hydrogen flight. And we're keen that the UK needs to take part in that and needs to keep pace with the action we're now seeing across aerospace and aviation.
Okay, and you did talk about the space sector in your presentation, but you said that the requirements are different. Do you think there are opportunities for others to come into the sector as well as later exploitation in other areas?
Yes, I think this is a disruptive time for aerospace and aviation, and I think we should look to read across capabilities across industries, look what knowledge is already out there, and space is one example. And we've spoken to a number of companies who work in that arena to read across those capabilities, the knowledge, tools, methods that already exist. But as I said, there's still a significant technology step in the different requirements, the different attributes of what we need to achieve for aerospace. But equally, looking forward, if we develop some of these new technologies, I think there is space to apply those new capabilities across industries as well for a number of those. So I think we can draw from industries of what exists today, but we can also exploit many of these technologies through multiple industries later as well.
Okay, thank you. And I think one of the really exciting things about the FlyZero project is how many different angles you've looked at this from. So, Chris, you were looking at the airport operations, and both Simon and Mark have referenced how much investment might be needed between now and adoption and utilization of some of these technologies. From an airport perspective, what do you think are the greatest challenges that they're looking at there?
I think it's the future uncertainty. I think, and Simon alluded to this as well. There's multiple fuel systems, so airports go from having sort of one system of fuel to potentially having kerosene, SAF, hydrogen, and electric as well. So the investments for these are huge. So you need some confidence before they can invest the money. You need the confidence to know that it's the right thing. They're backing the right option. So I think there's a long lead time for infrastructure as well. So we need to start planning today in master plans. So we need the confidence that these things are definitely coming. So I think it's really having some commitment behind the technology so that airports know that it's not just a paper idea, that something's actually really coming. And then it can start to working to develop these as well. So it's just, I think, continued collaboration is essential. We've worked with 5 airports during this project and had great engagement from them, and everyone's really keen to be working on this. So I think it's it's part of keeping all this together with the different sectors. I think is really important. I mean, on a technical level, I think the thing we found really, the refueling is where from a safety point we need to be running tests and developing that. It's quite a challenge. And then when we get to sort of hydrogen systems, the sort of cryogenic nature of that, I think, is going to be a real challenge. And the sort of the unique thing for aviation, I think, is going to be the amount of liquid hydrogen. So it's that liquefaction capability and the power to go with that as well. I think for airports is going to be a real challenge. So plenty of challenges, but hopefully solutions to all of them.
And so, I mean, you're referring to a number of sectors there that are all really going to have to be involved in the development of this. As FlyZero, you're the leadership team. So, how did you find bringing together so many different parts of the ecosystem, I suppose, because it goes beyond sectors and beyond just industry?
Yeah, so I think this has been personally, I think this has been one of the most interesting elements of this program. And the fact we've been able to bring together a team of 100 experts, both secondees and independent experts, and work with a whole range of different companies and organizations, going through the university network or the research organizations, going to small companies and large industrial players, has meant there's been a lot of useful exchange, a lot of power in combining the knowledge from these different organizations. And that is really necessary as well, as Chris was saying, because of the multidisciplinary nature of the challenge here, going from engines to aircraft to infrastructure, right back into fuel production, and even in considering the green power generation network. So it's been a real challenge, but it's meant we've had to bring together many different organizations with different capabilities. And that's really been a huge learning exercise for everybody.
So, Sophie, could I just add to that from my perspective as well, because it's and I completely agree with absolutely everything that Simon said, and I think for the leadership team it's been refreshing as well to get a number of different perspectives. Several of us from fairly large corporate organisations, and it's been fascinating, as I said, refreshing to see how other organisations work and bring different angles, views, and perspectives to the aerospace industry. So yeah, it's been great. It's been great.
Yeah,
Okay,
from my perspective,
oh, sorry, carry on.
I was going to say, from my perspective, I think it was working with external organisations as well. So working with the airports, with airlines, we had a number of consultants involved with this as well. And it's just, we had huge collaboration and everyone was sharing ideas, and it was just really, really helpful.
Perfect. And I do apologise, I didn't mean to cut you off there. I've got a question for you actually, Chris, with relation to the trucks delivering hydrogen to the airports. Why would it be delivered by trucks? Is it not feasible to look at something like pipelines?
I mean, to start with, we're looking at trucks because it's delivering its liquid hydrogen, so we can't deliver that in a pipeline because you can only liquid hydrogen you can only transfer for short distances. So it would have to be in a tanker for those initially. But I think it's then we get to a point where we get too many tankers. So for a large airport, we're looking at 500 deliveries a day of liquid hydrogen. So we can't do that.
Yeah.
So that's where we have to go to a pipeline. So we go to a gas pipeline for that. But it has to be gas in the pipeline. If it's liquid, it has to be in trucks, really.
Right. Okay. Thank you. And just to refer back, there was a conversation during one of the videos around also needing to maintain pace with ultra efficient technologies as well as zero carbon. Whilst you're waiting for the industry to essentially be able to move forward into hydrogen technologies, where would you say the priorities are in terms of needed efficiencies?
So I can,
Well,
Sophie, I can take that from. So certainly, I mean, as the title says, I was responsible for the airframe, so you can infer from that aerodynamic structures. And I think the good news is for the community in the UK is that lots of what we do today will still be applicable tomorrow. So the need to have lightweight, rate capable, efficient aerostructures will continue. There are instances where there'll be things that are specific to LH2 fuel, but in many instances, a lot of what we do today will continue. So we can continue down that path with no fear and at very low risk, in my opinion, Sophie.
Okay.
Simon, you're going to say sorry.
Yeah, so I completely agree. So we need to continue to look at lightweight structures. We also need to continue to look at efficient powertrains and propulsion systems as well. As I alluded to, as we project forward, we think across all the different fuel options, there's a real risk that the cost of producing those fuels and potential of taxation, etc., could drive the price of fuels up in the future. So we would want to minimise the end use price risk from that by continuing to improve the energy efficiency, minimising the losses in the systems. And that's the case for today's types of fuel systems. And equally, that would be the case for future hydrogen and SAF fueled systems as well. And we think there's a large amount of read across in developing improved propulsion systems, improved architectures, and increasing efficiency of those systems for the future.
Okay, thank you. And I'm just going to ask one last question. It's probably directed at Mark. There are a couple of people noticed that David showed the concepts with dry wings, and they really wanted to understand the weight influence of dry wings and why you'd gone down that route.
So the necessity for dry wings is, as Simon said earlier in his presentation, is more to do with volume of storage. So to carry the necessary volume of liquid hydrogen, we just don't physically have that volume required in the wings thrust. So hence the necessity to put the tanks in the fuselage, and that drives effectively what we've referred to as essentially dry wings. So wings with no fuel as we would know it in aircraft today. And that opens up a really a new design space for aerospace businesses. It's something we've touched on very lightly in FlyZero, and it needs a lot more exploration, and is one of those aerostructures technologies which is unique to LH2 aircraft. As we all know, it's kind of curse and cure. Today we use kerosene to provide bending relief in wings. We won't have that opportunity with future propulsion systems if they prove to be LH2. But it will provide the opportunity possibly for more aerodynamic and clean wings. So in summary, Sophie, more work required in this area, definitely.
Okay, and I mean that's a bit of a theme. You know, this was a feasibility study, and
Indeed.
so in your recommendations, you've pointed out a number of areas that you think further work needs to be done. If I could just ask each of you, what, from your perspective, what would be the main thing that you think needs to be taken forward as a result of this project? Mark, if I go to you first.
Yeah. I mean, I won't steal anybody else's thunder, but for me, it is around, from an aerostructure standpoint, the dry wings and the exploration of that space. It's critical and vital to the technologies going forward.
Okay, Simon, from your perspective.
Yeah, so I think to take this to the next level, I think we need to look at how we could go and do testing using real hydrogen, be that burning hydrogen, putting hydrogen into fuel cells, and the storage and delivery systems for hydrogen. So I think an investment in infrastructure in the UK to allow us to do that type of testing, to be able to do that rapidly and flexibly and safely as well, is a key next step. And then we can start to plan out an accelerated journey for getting this learning, validating our methods and assumptions from the concept study we've done on FlyZero.
Okay, and Chris, finally.
Yeah, I think it's very similar to Simon. Really, I think it's starting trials, because much of what we did was desk exercise, and particularly around safety. So we really need to start testing that, and because the fuel safety zones are critical in the process, I think. So we really need to do more on that as well, and then just starting to look at the rest of the technology in more detail, things like the hydrant and the aspects.
Okay, thank you. And thank you all for joining me for this discussion. I know you're going to be around later on. Please, if you did ask questions on Slido and we haven't got to them yet, please keep asking. We'll be coming back to that. We're going to take a 5-minute break now. There will be some videos playing. They're the same videos that we played in break 2, so don't worry if you miss some of them. You can always catch them again later on, and we will see you in 5 minutes. Thank you.
FlyZero has identified 6 revolutionary technology bricks which are critical to realising hydrogen-powered flight. These range from hydrogen fuel systems to gas turbines to fuel cells. The UK is world leading in areas like wings, fuel systems, heat exchangers and aero engines, and so we can bring this expertise to bear on decarbonising aviation. To enable this, the UK needs to establish a programme of mission-led research and development into hydrogen aerospace technology. It needs to be done in close strategic partnership between industry and government, and the Aerospace Technology Institute is ideally positioned to take a coordinating role. On top of this, the UK needs to work with partners around the world in things like technology development, aircraft development, but also on airport infrastructure.
FlyZero has developed 3 novel aircraft concepts to illustrate the art of the possible. We've demonstrated that with hydrogen fuel, you can fly all the way from London to Auckland in New Zealand with just one stop. For hydrogen aircraft to take off, we need a globally standardised approach to hydrogen infrastructure, the safety regulations and government policy. That's the route to achieving safe and efficient operation with hydrogen aircraft. This also represents an excellent opportunity for the UK to play a leading role in the development of those critical elements.
Welcome back. Hopefully you managed to get a drink and perhaps see those videos, but don't worry if you didn't, they'll be in the second break. So to start our second part of today's webinar, I'm delighted to be able to introduce you to Chris Gear. He's the Program Director for FlyZero, and he's going to talk to you about the project. Chris, over to you.
Thank you, Sophie, and good afternoon, everyone. So great to be here. And I think you've just heard from some of my leadership team the amazing work we've been doing in technology. But I just want to describe some of the things that we've gone through as a group. So, we were challenged at the beginning of this program to look at something that's really huge and difficult to achieve, which is zero carbon emissions out of large commercial aircraft. And I have to say, we've done a tremendous amount of work, not only on the design of aircraft, but also how would you operate those aircraft? How would you build the infrastructure and any energy requirements to actually allow you to deliver those aircraft to the community, to the commercial aircraft market? I think what we've proven, though, is that aviation has two routes for net zero carbon by 2050. And if we are going to achieve that target of 2050, we need to do both routes. And the first route is clearly around the sustainable aviation fuel and making sure we have the capacity and production and industry in place to deliver those fuels to the existing aircraft that we see today. And the second route, which is also as important, is that we need to invest in liquid hydrogen technologies now to ensure that we can introduce those aircraft by 2035 and start to influence the commercial market. I think we've proven to ourselves that if we don't have both of those fuels in the system and operating by 2035, we won't achieve our 2050 targets on net zero. So that's the huge challenge we, the global aviation community, face. And at the same time, there's a lot going on in terms of how do we actually do that. Some of the things we've found is the integration across aerospace, energy, infrastructure and aviation is critical to achieve this, because everyone needs to move at a similar pace to make sure that we have all the ingredients necessary to fly a new type of vehicle with new fuels in it. And so we've done a lot of work. And if you look within our reports that are now live, you can see the tremendous amount of work that my amazing leadership team and also my secondees from the 13 contributing companies and my fixed term contractors have done to try and discover what are the key challenges that we all face and also propose some solutions to those challenges. Now, a lot of the work we have done is really on, looking at this and predicting what we think will happen, but it is backed up with modeling and simulation and actually the team's own internal knowledge of aerospace, because we have a vast depth of knowledge within the FlyZero team about aerospace industry, from the design of the aircraft all the way through to how you would refuel an aircraft at an airport. And that's what's been so amazing about the FlyZero program, is we were set a goal, a vision around zero carbon emission. The team that I managed to bring into this were all really enthusiastic about how to solve that problem. And that made a real difference to the quality and the depth of the resource and the reports that we are now producing. So I'm hoping that the community will find all of this to their benefit and will see the value that we've really given to you. We've also determined that there is a way of producing what we call a mid-size first pathway aircraft in service by 2035, which is looking at a larger aircraft than an narrow body, which would have a range of something over 5,000 nautical miles, but would be able to, in one stop, fly the 93% of all the global aviation requirements that you see today. And to us, this aircraft could represent the way of introducing a new fuel using the larger international airports as hubs to actually then develop the solution alongside the sustainable aviation fuel that you see today in existing aircraft. As well as that, we do think that the UK aerospace is particularly at risk in the wing and the propulsion and the fuel systems. And all of these are going to need investment because the technologies we're looking at will disrupt all of them. And if we're right in our predictions, in the long term, 2050 to 2070, some of these will become very much dominant in terms of the necessity to have changed that technology. We can also see that from an economic point of view, the UK will benefit hugely by investment in these technologies. And it will bring us into a position where we can lead on some of those technologies back into the community, into the global aviation community, and therefore ensure we secure and anchor technology in the UK, but also protect the jobs we have today and hopefully grow those jobs by being very much at the leading edge of technology. So there's a lot for us to do. And finally, there's one other key point that we've discovered in our analysis work, which is all around climate science. And this is vital in any mission on sustainability. I think we're very good at predicting climate science, but we need a lot more test and measurement data to finally validate it. And to me, that's one of the goals that we've used to FlyZero to do, is not only try and find solutions, but try and determine open questions that still need more work to be done. And so I'm really pleased that we're able to identify those open questions and hopefully open it up for the UK community and the global aviation community to go and focus on how you take the next steps at actually defining some of those solutions that we quite rightly have touched on, but we haven't been able to go into the depth that's needed to actually get to the final answers. I'd also like to sort of say that, I want to thank Bays and also the ATI for all their support to allow us to run FlyZero and help us fund it, but also set up the imagination to say, look, this is something that needs to be done. And I think that's been tremendous. The contributing companies and secondees and their knowledge and experience and the way they supported FlyZero has been fantastic. And also the fixed term contractors that we were able to bring in to fulfill sort of specialist roles that we needed within the group. So what you will find is we developed and brought together something in the region of 100 people. We have spent the whole year working from home in a COVID environment, yet I've actually created a group of people who have got the imagination to bring a lot of what we're talking about to reality, and are going to go back into their industrial companies and hopefully be ambassadors to what are the next steps for the future of global aviation. So I really want to thank all of them for all their hard work and effort to get us to where we are today. As well as that, we offloaded something like 61 packages out to universities, into academia, and into industrial companies, and even into catapults and research centers to try and get to some of the answers that you will see in our reports. And they were tremendous help and really showed the breadth the UK has in these type of technologies, and that can really bring it back into aviation and support the future. So thank you to all those people and Bays and ATI for supporting us and helping us get through this. As well as that, the FlyZero and the Jet Zero Council have worked closely to try and look at what is the zero carbon emission solutions. And I really want to say thank you to all those people who supported us through the advisory boards and the design advisory boards to make this a reality. It's been a fantastic journey. I think you're going to find some really amazing conversations going to go on some of the other topics we touched on, but hopefully you will enjoy what we've got. So really, this is a call to action for industry to recognize, we started the mission a year ago, and a lot of people would look at me and sort of say, surely we should just focus on net zero. But I think today there's a reality of feeling that, hydrogen, liquid hydrogen is important, and we need to develop those technologies further. So thank you for listening to me. I'm now going to introduce 3 more of my leadership team: Naresh Kumar on sustainability, Katie Milnes on industrial, and Mark Howard looking at the economics and commercial side. Thank you.
Good afternoon. Sustainability has been central to the FlyZero project, and we've done significant work to assess the full life cycle impacts from using hydrogen. I'm going to explain our key findings on CO2, non-CO2, and the broader sustainability aspects evaluated over the last year. The reports detailing the sustainability work are available on the ATI FlyZero website and includes our recommendations on future work, particularly on climate science. Let's start with total impacts. We know that hydrogen will eliminate tailpipe emissions of carbon dioxide. In this chart, we looked at the combined impact of CO2 emissions, water vapor, NOx, and fuel production. It doesn't show the impact of contrails, which I will cover in detail on the next slide. The chart measures grams of CO2 equivalent per megajoule of fuel energy as global warming potential over a 100-year period. We compared Jet A1 as well as sustainable aviation fuel alongside liquid hydrogen. Now, there are a number of production routes already approved for biosaf. For this comparison, we assumed a carbon saving maturity to reach 90% by the mid-2030s, even though current government requirements demand 65% minimum. This is so that we compare future developments in SAF by the mid-2030s, when we would expect hydrogen planes to begin entering service. In the case of power to liquid, this can only be carbon neutral if the carbon needed to make it is captured efficiently using processes such as direct air capture. Without carbon capture, current aircraft using power to liquid may not be able to achieve net zero. So, in addition to eliminating tailpipe CO2 emissions, this chart shows hydrogen is better overall on the aggregate of these non-CO2 parameters. Switching to hydrogen could potentially lead to a cumulative benefit, a global saving of over 4 gigatons of CO2 by 2050, which would increase to 14 gigatons by 2060. This is a huge prize, given that in 2019, global aviation emissions were just shy of 1 gigaton. But it is based on a mid-size hydrogen-powered aircraft entering service by 2035 and subsequent variants over the following decade. From a scientific confidence point of view, we're very sure about the CO2 impacts, but the scientific uncertainty is higher for the other parameters, where more work needs to be done on climate science. Another assessment, key assessment that we did was looking at the energy to produce the hydrogen. We found that 12% more renewable or low carbon electricity globally will be needed to produce and liquefy the hydrogen needed for aircraft worldwide. But if we compare this to power to liquid, to meet the same demand in 2060, power to liquid will need around 45% more electricity than just making the hydrogen. And it'll cost more, and it'll have an overall higher climate impact. So it seemed very reasonable that hydrogen offers the best solution in the medium to long term. Now, let's look at contrails. The climate impact of contrails remains uncertain, as shown on the radiative forcing chart in red, published by the Intergovernmental Panel for Climate Change last year. Contrails typically last for minutes or a few hours, so it's very much a short-term effect compared to CO2, which stays in the atmosphere for hundreds of years. Now, burning hydrogen generates around 2.6 times the amount of water in the exhaust compared to kerosene. So more contrails will likely form. Our study with Leeds University estimates that these will form at lower altitude, as you can see on the charts in blue. However, these contrails will have different characteristics from those nucleating around soot particles from Jet A1 kerosene, biosaf, or power to liquid. The contrails from water emissions will have lower optical density. The ice crystals will be larger, so will likely dissipate faster. And the Leeds modeling work indicates that because of these differences, the overall impact for contrails is likely to be less. There's one caveat to that, however. We need to verify by laboratory testing and possibly chase plane measurements some of these characteristics in terms of ice particle size and dissipation rates. This is recommended in our future work and is fundamental to improving the understanding of climate science. Now, we know that some contrails could be cooling, those during the day, but the overall effect is one of warming, particularly from contrails in the evening and during the night. There are strong prospects for navigational contrail avoidance. A number of organizations are exploring this quite aggressively, including Eurocontrol, Satavia, DLR, and a number of airlines. with a recent trial ran over the Maastricht area reported 2 or 3 weeks ago. There is some encouraging indication that half of the contrails could be avoided with 1% fuel penalty. And if this was using hydrogen aircraft, there would obviously be no additional CO2 emitted during that diversion. The avoidance of contrails would lead to an almost immediate reduction in climate warming as a result. However, successful implementation will very much depend on accurate weather prediction of ice supersaturated regions where contrails may form, so definitely more research to complete in this regard. To complete the picture, we also looked at other non-CO2 effects. On oxides of nitrogen, we estimate that this will be 50 to 70% less for hydrogen-powered gas turbines compared to today's technology, and fuel cells don't produce any NOx. Regarding particulates, because there's no carbon in the hydrogen fuel, there won't be any soot, but we may get a very small amount of trace lubricating oil seeping from engine seals, which might generate some particulates. Regarding sulfur, there won't be any oxides of sulfur, which today comes from the sulfur that exists in the Jet A1 when that is processed. Now, earlier I mentioned that hydrogen combustion will produce 2.6 times the amount of water in the exhaust. So we've also looked at the direct impact of water vapor, which can act as a greenhouse gas. This is important in the stratosphere, above the tropopause, where large commercial aircraft will fly into, particularly during winter months when the tropopause is lower down. The good news is that FlyZero concept aircraft are anticipated to fly at the same altitude or slightly less than current aircraft. The total climate impact from this water vapor is around 2% of the 2 to 3.5% of total aviation impact. But even so, further research is recommended here also. Now, on noise, our work with Southampton University indicates that FlyZero concepts will be competitive on noise compared to other future aircraft, and will be able to meet the next global noise standard following Chapter 14. That's good news. Finally, as part of the full life cycle analysis, we also looked at the environmental impact resulting from materials, manufacturing, and the maintenance of aircraft. Although this is around 1% of the impact relative to emissions from the use of the aircraft in service, we wanted to make sure that we identify opportunities where the carbon footprint may be further reduced in the future. FlyZero concepts will require new and novel materials and processes. So it's important that productionization and supply chains build best practices to improve circularity for new technologies such as cryogenics, fuel cells, and the like that will be needed for the next generation of aircraft. This is recommended through deploying design for sustainability methods, all the way from raw materials through to end of life. By the way, comprehensive list of materials and processes are covered in our reports, including work we did with Strathclyde University on this important topic. So, to wrap up, our work on CO2 and non-CO2, backed up with a full life cycle analysis, gives us confidence that the use of hydrogen on the proposed FlyZero concept aircraft can help to truly decarbonize aviation. The sooner this is done, the sooner we can realize significant CO2 reductions and thereby contribute to not only the UK net zero goal for 2050, but all across the globe. Thank you.
Good afternoon. My name is Mark Howard, and I have had the pleasure of heading up the commercial strategy team for the FlyZero project. I'd like to take you through a whistle-stop tour of our market forecast, the options for exploitation of zero carbon aerospace technology, and a view of the economic reasons for acting. FlyZero has undertaken a detailed market study and determined a global market forecast. The baseline forecast broadly matches that of Airbus and Boeing, issued in Q4 2021. But we've also taken an additional, more conservative view, looking to account for an incomplete recovery from the COVID pandemic. This more conservative view actually aligns well to the Oxford Economics analysis, which was undertaken by IATA, and in summary, delays the market by approximately 5 years. However, all of the market forecasts show a market that is due to more than double over the next 20 years. For the market forecast, we've broken the market down fairly traditionally, but provided a distinction for the mid-size aircraft as a 200 to 300 seat wide-body aircraft with a scheduled sector distance of up to 5,250 nautical miles. The narrow-body, mid-size and wide-body segments collectively accounted for 93% of CO2 emissions in 2019 and are projected to account for 96% of CO2 emissions from aviation in 2050. Now, the aviation sector emitted 920 megatons of CO2 in 2019. And if we do not act with zero carbon emissions aircraft or high volumes of sustainable aviation fuels and direct air capture of CO2, this will grow to 1,540 megatons of CO2 in 2050. So let's put this into context for the UK. Assume that other CO2 emitting sectors act and aviation doesn't. Aviation is likely to account for 39% of the UK CO2 emissions in 2050, which will not be acceptable socially, nor, we believe, economically, as restricting aviation will hold back the economy. You can see that the market value associated with a more than doubling fleet, with many aircraft that will need to retire, is actually quite frankly enormous. We assess that at $3.6 trillion. And this isn't based on ticket prices of aircraft. This is based on realistic prices of what airlines are likely to pay. Of course, the market is dominated by the narrow body, but we must remember that these are the current and future cash cows for the airframers. Whilst the project was not asked to look at sustainable aviation fuels or SAFs, one of our primary considerations was to assess the future cost of fuel to enable an understanding of the operating economics. This has to be considered on a dollars per megajoule of stored energy basis, as liquid hydrogen is 3 times lighter than kerosene. And in the graph, we've aimed to normalise this to equate to an equivalent ton of kerosene. We've essentially taken many external studies to compare green liquid hydrogen against a blend of many forms of SAF. All of these studies take differing but similar assumptions around volumes of available SAF over time, with biomass representing 30 to 40% of demand but maximising out by 2040, and there are aggressive forecasts of PTL maybe achieving 50 to 60% of capacity by 2050. So we've adopted a blend of the different forms of SAF as they become available, and of course tax kerosene to develop our integrated cost forecast. We have used carbon taxation forecasts from the Department for Business, Energy and Industrial Strategy, but we believe that the industry can expect to have carbon taxation applied on a more global basis. There could be a good solution here if the tax generated was used to support investments into the sector to accelerate the availability of technology and ultimately zero carbon aircraft and the required supporting infrastructure. From this assessment, we've concluded that the cost transition for liquid hydrogen to be cheaper than a combination of taxed kerosene and proportionally taxed SAF is around mid-2030s. To assess how good the FlyZero aircraft concepts are, we have compared energy demands to achieve typical sector emissions against current conventional hydrocarbon aircraft and against an equivalent new clean sheet design SAF burning aircraft. This chart is showing the narrow body comparisons. The FlyZero hydrogen gas turbine powered narrow body concept, or FZN, we believe is on par with a clean sheet SAF burning new single aisle. The ship fuel costs are expected to be cheaper than that NSA aircraft by 2040. And even when we start to account for the additional maintenance costs associated with the more complex system and new systems that the cryogenics bring, we found that the direct operating costs per RPK, per revenue passenger kilometre, are also less for the hydrogen aircraft. The conclusion that we've drawn is that the operating economics of these hydrogen aircraft are both attractive and superior and will help the market penetration. We have looked at a number of market entry scenarios. Our view has been that the narrow body fleet are cash cows for the OEMs, so we suspect that these aircraft will more likely follow a lead aircraft that proves the market attractiveness. Consequently, we are sharing two of the scenarios we've considered. The first being an ambitious mid-size first strategy, seeing a mid-size type aircraft enter into service in the early 2030s to de-risk the technology introduction, which would then quickly be followed by a narrow body adopting downscaled technology from the mid-size, and we believe that the market penetration could be really quite significant. In the second scenario which we've described as the regional first approach, there is a more likelihood of a conventional narrow body to be launched around 2030, which would delay a hydrogen narrow body for a generation. In this instance, the market would demand a large amount of SAF and actually large amounts of PTL SAF by 2050 to meet the net zero targets. Our challenge to the aerospace sector is therefore to be bold. We believe that large civil aircraft should be the priority, and they will abate more carbon dioxide per flight, leading with a mid-size aircraft will have the greatest positive effect on CO2 emissions. We collectively need to ensure that all actors step up, global industry, global governments, and collectively look to accelerate the delivery of zero carbon aircraft. This acceleration making flying ever more affordable and ever more green. But let's be honest, introducing hydrogen aircraft is not going to be easy. The industry has a significant coordination challenge to overcome. There's not only the generation of green electricity, but also the generation of the hydrogen distribution infrastructure to get it to the point of use. And then, of course, we need to be able to convert a number of airports to be hydrogen ready, on top of the global OEMs developing and producing the aircraft, carefully introducing them into the fleet without damaging the cash cows that keeps the OEMs in business today. But we believe the prize is great. From this chart, to tackle emissions, we need to focus on large civil aircraft. To address the infrastructure conversion, the mid-size aircraft would demand the least, but require significant global coordination, ultimately acting as feeders for narrow-body introduction that would naturally follow. Ultimately, we need to look to international collaboration to achieve the goal of decarbonisation. And this is not just for the aerospace sector. We have a coordination and collaboration challenge across energy, aerospace, and aviation. And finally, I'd like to try and explain the economic value of investing in decarbonisation. This chart reflects the aviation sector, basically the airlines, the airports, and the airspace management, showing the UK jobs and gross value add that this sector brings to the economy. The bubble size represents the number of people flying, ultimately, the RPKs, revenue passenger kilometres. And the bubbles are depicting each of the FlyZero scenarios, the mid-size first and the regional first. but also a Jet Zero consultation scenario, which effectively reflects a quantity of 5% SAF in the fuel mix by 2050, with market-based measures ultimately restricting aviation to keep CO2 emissions down. We believe that the more people fly, the better it is for the economy. This is true for any economy. Aviation connects people. It brings social benefits, economic business, tourism, and we've seen from the forecast growth that people want to fly. It just won't be at any cost. So these market-based measures that restrict flying are represented by this continuation of current trend scenario. And that ultimately shows that restricting aviation to reduce emissions does not come without a cost to the economy. The reduced RPKs, revenue passenger kilometres, result in less jobs and GVA. It is therefore not free decarbonisation. Zero carbon aircraft can help mitigate this effect. So in summary, the market is growing. We believe zero carbon aircraft have superior operational economics, and they avoid the longer term challenge of CO2 effects in the atmosphere. They also avoid significant volumes of PTL SAF, which means it's probably cheaper for the operators to run their operations. The mid-size aircraft leading with that would minimise infrastructure, but ultimately our big message is that economically restricting aviation is not free decarbonisation.
Hello, my name's Katie Milne and I'm Head of Industrial Strategy on FlyZero. I've been working for the last year with a brilliant team of people from across industry on the UK capability in hydrogen aerospace technology and what action we need to take. I have technologists in my team looking at manufacturing, materials and compressed design and validation, and they've put out papers alongside the technology roadmaps. But today I'm going to focus on capability and actions. So Simon Webb showed this slide earlier. It shows the hydrogen aerospace technologies that need to be developed in order to realise hydrogen fuel cell electric and hydrogen gas turbine aircraft. The UK has world-leading competency in aerodynamic structures and wings, in thermal managers and heat exchangers, gas turbines and thrust generation and fuel systems. However, it has a big gap in terms of cryogenics and hydrogen behaviour that it really needs to address and build capability in order to develop these types of technologies. The UK is also extremely competitive on electrical systems. Both the incumbent aerospace players are building electrical capability very rapidly, but also companies who've been looking at automotive, developing electric motors, for example, for the automotive sector, are now beginning to look towards the aerospace sector. And electrical is relevant for any future aircraft, whether it's powered by future sustainable aviation fuels, drop-in alternatives to kerosene, or by hydrogen. And so this is an area which the UK should really concentrate on. We have activity around integration of fuel cell onto aircraft, but the fuel cell market will be much bigger than the aerospace segment. And so there's space here for concerted action, which is cross-sector in terms of development of fuel cell technology, similar to that for the Faraday battery challenge that we've had on batteries over the last several years. And then tanks. There's a great deal of capability in the USA linked to its space launch capability for hydrogen tanks. And there's also research centres in France, Spain and Germany now linked to the Airbus Zero-E programme. The UK, though, has strong capability around composites manufacturing, and one of the tank options for the future is composites. So the UK could compete there, but we need to move quickly. Here I show a development pathway for the hydrogen gas turbine architecture. Very high level. There's more detail in our technology roadmaps, in our verification and validation report. But I've put it up here so that I can just talk briefly about test infrastructure. These new systems, these hydrogen-based systems, will require new test infrastructure, and they'll have new types of tests as well in order to demonstrate safety and performance. And that will be at the system level, at the aircraft level. We'll need tests of emissions in flight, and at the system level, we'll need tests of refueling. And if the UK builds that capability, it will help accelerate our industrial players, but it will also help with collaboration as companies around the world would want to work with us and to use that infrastructure. We believe the window of opportunity is short. If we assume that the larger aircraft are going to come into service in the mid-2030s, and that the smaller and hydrogen electric aircraft will actually could potentially be even earlier than that. Some of the players are targeting the mid to late 2020s. And if we take into account the fact that there is a lead time on that aircraft development program, and that for the aircraft development program to launch, they need all that critical technology to be to already been demonstrated as mature in a representative environment. So at technology readiness level 6, then working from right to left, we need to achieve technology readiness level 6 by around 2025. That gives the UK a very short 3-year window of opportunity to move and to develop these new solutions. So what's the potential opportunity for UK aerospace? This graph shows the 2019 baseline and then 3 different projections of the future, and they're linked to the level of investment from UK industry. So in the most pessimistic scenario, we do not move, but hydrogen aircraft come to market. That is a failure to act. And we believe that by 2050, the UK aerospace sector could then be in decline. Obviously, this assumes that hydrogen aircraft do come to market, but we believe on FlyZero that they're highly feasible. And so if other countries break through and we're not with them, then hydrogen aircraft will be increasingly winning market share and the UK aerospace will not be in it. The alternative is to invest, of course, and to move, and we're beginning to see increasing evidence of UK industry players doing that, so ramping up now towards a good critical mass. A slower level investment would allow us to maintain current market share through this technological disruption, but there is an opportunity whereby we maximise our investment, we maximise the rate at which we move, and we actually manage to increase UK strength in aerospace, take advantage effectively of this technological disruption for economic benefit. And in that optimistic and ambitious scenario, we believe we could grow our UK aerospace sector to 150,000 jobs by 2050 and increase our market share from what is now 12% to 19%. The cumulative global zero carbon aerospace market from 2030 to 2050, in our most ambitious scenario, where the airframers develop large aircraft rapidly, so bring them into service in the 2030s, is $2 trillion. That compares to a total global aerospace market of $3.6 trillion. And by 2050, the relative size of the zero carbon market, the hydrogen market, compared to the other part will be increasing at pace. What we wanted to show here was the potential UK share of that zero carbon aerospace market, so this is higher because we're just looking at zero carbon, not the entire global aerospace market, and how that could be broken down relatively by BRIC. So what is their relative potential value to the UK? International players are moving rapidly. For hydrogen gas turbine aircraft, Airbus has announced its Zero E programme. It's collaborating with CFM, which is a collaboration between General Electric Aviation, US company, and Safran, a French company. The Brazilian company Embraer is exploring concepts in its Energia programme. For hydrogen fuel cell electric aircraft, challenger companies are leading the way, and we have some of those in the UK, Zero Avia, Cranfield Aerospace Solution, and GKN Aerospace on their H2 Gear programme. Just to give an idea of the level of activity overseas, we've put together this graph that shows public funding in clean aviation projects over the period 2022 to 2024 across leading aerospace nations. And you can see that they're investing in the order of hundreds of millions of pounds a year, up to about half a billion per year in some countries. Another perspective is the relative level of patent activity by country, and this picture shows it in technology areas relevant to hydrogen aircraft. And you can see in the patents that there's some countries who aren't Aerospace power is beginning to do a lot of work in technology that could then be exploited on aircrafts. So South Korea in particular, but also Japan is very active, Germany is very active. And these countries are seeing the opportunity of this technological disruption and moving. So the UK has really strong competency in areas that are relevant to hydrogen aircraft. If the UK aerospace sector uses its knowledge, then it could help accelerate the time to market of hydrogen-powered aircraft. But similarly, if we want to win systems and share on these future platforms, then we need to move rapidly. Industry and government need to work internationally to help bring large hydrogen-powered aircraft to market as soon as possible. Naresh and Mark have both talked about the benefits of accelerating those large narrow-body and mid-size aircraft. We need to shift our mission. This year, FlyZero has been looking at the feasibility of a range of zero-carbon technologies. We've concluded that hydrogen technologies have the greatest potential. So now, going forward, we need to move our mission to being development of those hydrogen aerospace technologies to TRL 6, demonstration and representative environment, by 2025. We need to ring fence hydrogen. We need to ring fence budget for hydrogen aerospace technologies and carry out directed R&D to make sure that we stimulate enough activity in industry. We also need to carry out early stage or promote early stage R&D in companies, because some of this technology is currently at much lower levels on the TRL ranking, kind of about 2 or 3, some of it. And there's lots of potential for breakthroughs from different directions. So we need companies to have space to explore, to learn, to fail fast and learn quickly, and be betting multiple pathways forward, so that then we can make sure that the UK maximises its chance of having winning solutions. And as I said before, we need to invest in test infrastructure and demonstration platforms, so UK supply chain companies can demonstrate the maturity of their technology. Rate-capable manufacturing technologies need to be developed in parallel, and we need to just look at compressing overall the time to market. To do all of this, we need to create strategic partnerships within UK aerospace, but also building collaboration internationally, because aerospace aviation is a multinational activity, and we need to coordinate beyond aerospace with aviation and hydrogen fuel producers. We believe that there's a need for a cross-sector hydrogen technology centre, or to leverage a network of existing centres to look at things like how hydrogen is handled and distributed, at materials, and the impact on climate science. And this could act as a skills sandpit and really fill that gap that I was talking about earlier. And finally, we need financing for capital-intensive projects, test infrastructure, pilot lines, and production facilities. It's been a really insightful, exciting year working on FlyZero, and at this point it's time to hand over this baton and these recommendations to the community and for the UK aerospace sector to take them forward. Thank you very much for your time.
Hello, I'm Laura Cuss, Head of Strategy at the ATI, and I'm joined by Katie Mill and Mark Howard, who we have just heard from. So on behalf of everyone, thank you guys for the presentations. The content was sort of thought-provoking and insightful, and I know it's just a small subset of the information in the reports. Slido is open for the audience. If you want to ask some questions, we'll try to keep an eye on it. If they're not asked now, maybe at the Q&A at the end. But I have a few questions. So you've both highlighted that reducing emissions in aviation is a global problem. And then, we have those that say that as long as a solution is found, the UK will benefit for net zero and the continuation of the aviation sector. But therefore, Katie, why is the UK's role so important?
The UK's got really leading aerospace capability globally already. And so if we don't move, we're effectively withdrawing our 100,000 workforce out of the game. We've got, around 25,000 engineering and designers in the UK, and that doesn't seem like the right thing to do given the climate change imperative. So that's the first thing. But also the areas that we're competent in are highly relevant to the systems that need to be changed to realise hydrogen aircraft. So wings, and then the propulsion system, gas turbines, we've got strengthened electrical systems. So the UK can really make a difference in terms of adding to the quantity of effort going on worldwide.
Okay, thank you. And Mark, your presentation was sort of showing us and prompting us that we need to think a little bit wider than aerospace. So, airlines, airports, airspace, but also from an energy perspective. What insights did you gain from this analysis?
Yeah, so I guess first of all, I'd like to thank the airlines and the airports we work with, because they really helped bring some of our questions to life, and that was really key to the findings that we eventually ended up with. I guess ultimately what we have here is a system of systems problem. We ultimately need to reshape the value chain, and as you said, Laura, this will require quite a significant amount of collaboration and coordination on an international basis. So that becomes really sort of a big imperative. But as Naresh described, we have a win-win situation opportunity here. We have the opportunity with hydrogen aircraft for CO2 abatement, having the right amount of investment, as Casey described, in terms of research and development, and of course, ultimately trying to make flying more affordable. And the more people fly, the bigger the aviation sector is, more businesses generated, more tourism, etc. And we can do that without environmental impact. I think it's also fair to say that, coming back to sort of the fuel cost analysis that we've done, that is very much driven by the cost of electrical energy reducing, and that actually becomes quite an important point here. In the future renewables, global forecasts are suggesting that those come down quite significantly, and that helps bring that competitiveness against taxed kerosene. Now, our analysis admittedly was done against both taxed and untaxed kerosene, and that transition in the mid-2030s is against taxed kerosene. However, given the instability that we see today in the world, you can start to see that even ordinary untaxed kerosene will start to become actually rather expensive in the future. And I think from a perspective of energy security and resilience, the opportunity that hydrogen manufactured SAFs brings an opportunity to actually bring that that price instability under control.
Okay, thank you. And we've got some questions really that are sort of asking and building on that need sort of for, I guess, the global coordination. So I guess the question on, how we feel that globally everyone is aligning to liquid hydrogen being perhaps the solution and the answer for what we need.
Do you want me to say that one, Casey? I think, essentially, I guess we're at the start of a journey. Yeah, there are differing views today in terms of where where liquid hydrogen is. Clearly, Airbus has taken the view that is the answer. The Zero E program is focused on liquid hydrogen. It's a bit uncertain today in terms of where Boeing are and where other organisations are, but even the likes of Embraer are looking at sort of longer term hydrogen solutions for their potential regional, looking to have that as a future development. So I think we're at the start of a journey today. Yeah, it's not decided, but I think our analysis has tried to re-emphasise the fact that we think this is the future. And and that's from a commercial and sustainable perspective.
Okay, Katie, anything you want to build?
No, not particularly. I mean, the thing that strikes me, I suppose, is that that the amount of activity around hydrogen fuel cell electric in Challenger aircraft is really high at the moment, and scaling to those narrow body and mid-size aircraft is quite a challenge, because you're going to have to convert to gas turbines, and the cost of investment to get those larger aircraft is much higher. You're talking about going from
single billion figures up to tens of billions in order to achieve the larger aircraft. And so to create those larger aircraft, you really do need a global supply chain, a global effort. And I think it's, how do we take the activity we've already got in the UK, which is on hydrogen fuel cell electric, and how do we scale that up and make it relevant? How do we take things across from other sectors internationally? How do we forge relationships and partnerships to accelerate the rate of entry of those large aircraft as rapidly as possible?
Okay, thank you. And Katie, you've shown sort of with the right level of investment, there is a significant benefit for the UK for jobs. We have a market that seems to be doubling and GVA increasing by 3 times. Why isn't the job growth higher?
Well, aerospace is already ramping up its kind of production rates. It's increased significantly over the last 20 years, and they're targeting. So both programs are targeting the order of rate 100 for narrow bodies. That's 100 aircraft per month. In order to achieve those doublings effectively of production rate, then they can either, of course, expand their footprint and their workforce, or they can increase productivity. And because aerospace is a lower volume, lower rate industry, the opportunities for productivity and automation are very high. And if we invest and we can lead the world on productivity, then we can be competitive. We can also begin to look to bring more of the onshore, more of the manufacturing. That means we'll be more in control of our emissions. We won't be sending them overseas. And in general, it just is a good news story of green jobs and onshoring for the UK. So an increase in jobs, but not as high as, due to productivity, as the increase in revenue, effectively.
Okay, grand. And I guess that there's going to be some other challenges, I suppose, around the job. So, as we pivot to hydrogen and new technologies, and we've got the increased jobs, what does that mean, do you think, from skills perspective in the manufacturing sector and the aerospace sector?
Well, we've done a very high level skills analysis through FlyZero. It wasn't central to the project, but we've kind of laid out what we think the skills demand trigger will be through a report that will go out next week. And really, there's 2 kind of points of consideration. One is that for some of the skills around electrical fuel cells, we're really going to be in quite a lot of competition, I suppose, with other sectors for those skills. And then the other is that we have a big gap that I was speaking about earlier around cryogenics and hydrogen. And I think that gap's bigger in the UK than it is in other countries who are moving or who have the potential to move on hydrogen aerospace. So we really need to do something very concerted. This isn't to fill the cryogenics gap, isn't necessarily like a massive upskilling program of thousands, hundreds of thousands of people. What we really need is those specialists now, to grow those specialists or to bring them to the UK that can then seed and spread their knowledge, teach others, learn by doing, learn through research projects at this stage in the cycle, and then we'll be able to roll out a much more structured upskilling over time. Because this is a 10-year journey really overall.
Okay, thanks, Katie. And clearly, so much fantastic work has gone into the project by your teams and the reports you've produced. So I guess it's going to be hard to sum up, but Mark, what's your key point of action that you would say for the UK sector?
Well, okay. I'll be really quick because obviously time, but I think clearly SAF and hydrogen have a role to play here. Yeah, absolutely key that we push both. We do think that zero carbon hydrogen is the future, though. Ultimately, we need to accelerate the availability of technology. We need to bring forward the introduction of the aircraft, and ultimately, we think there's a win-win opportunity there to actually sort of get your CO2 abatement, improve the output for the economy, and improve jobs, as Casey described.
Okay, a great call for action. I guess we could go with loads of questions here, but we're due to take a break. So again, quick 5-minute break. So we've got some videos that will be playing in the background, but we'll be back with the live final part of the webinar in 5 minutes. Thank you.
Thank you.
FlyZero has identified 6 revolutionary technology bricks which are critical to realising hydrogen-powered flight. These range from hydrogen fuel systems to gas turbines to fuel cells. The UK is world leading in areas like wings, fuel systems, heat exchangers and aero engines, and so we can bring this expertise to bear on decarbonising aviation. To enable this, the UK needs to establish a programme of mission-led research and development into hydrogen aerospace technology. It needs to be done in close strategic partnership between industry and government, and the Aerospace Technology Institute is ideally positioned to take a coordinating role. On top of this, the UK needs to work with partners around the world in things like technology development, aircraft development, but also on airport infrastructure.
FlyZero has developed 3 novel aircraft concepts to illustrate the art of the possible. We've demonstrated that with hydrogen fuel, you can fly all the way from London to Auckland in New Zealand with just one stop. For hydrogen aircraft to take off, we need a globally standardised approach to hydrogen infrastructure, the safety regulations and government policy. That's the route to achieving safe and efficient operation with hydrogen aircraft. This also represents an excellent opportunity for the UK to play a leading role in the development of those critical elements.
Hi, welcome back. So you're now in the third and final part of our event today, and we're going to be looking at the FlyZero experience, and then we're going to be holding a final Q&A with 7 of our presenters today. So if you do have any more questions, please get them into Slido so that we can deal with those after the next session. So you're about to hear from FlyZero's Head of Project Management, Chris Hughes, and he will tell you more about the reports that have been produced by FlyZero and how you can access them. We're then going to hear again from Mark Willier, the Chief Engineer Airframe, as he discusses his experience of FlyZero from a leadership team perspective. And then there will be a discussion between Bethany Hall and James Cole on their experience of being part of Team FlyZero. So I hope you enjoy the next session, and I'll see you again for the Q&A shortly.
Good afternoon. My name is Chris Hughes, and I'm the Head of Project Management on the FlyZero project, seconded from Spirit Aerosystems. I'm going to share with you our suite of project reports and how to access them. FlyZero has produced a suite of reports documenting our findings and recommendations. There are 37 open source reports and technology roadmaps, 21 technical reports, 66 reports from our work packages placed with industry and academia, and supporting presentations and models. The open source reports are available to everyone via the ATI website, and to access the technical reports, work package reports, and supporting information, your organization needs to pass a simple access test. These are our open source reports. The primary energy source and UK industrial capability and opportunities were published earlier in the project. You can see these on the left-hand side of the slide. The main body of reports are being published this month, and most of these reports are live on the website right now. Our executive summary shares our findings and recommendations. Our main vision report then provides further details on these findings, why we are making our recommendation, and provides a high-level summary of the suite of reports below, which cover sustainability, concepts, roadmaps and cross-cutting technologies, industrial economics and skills, and project innovation management. To access the reports, visit www.ati.org.uk, select Resources, and then FlyZero Reports. Check that you understand the license agreement. The web page then explains the 2 categories of reports, open source and restricted. The open source reports can be accessed by anybody and provide a broad overview of our findings. To download the open source reports, simply scroll down the page and select Downloads. The restricted reports are a series of more detailed and technical reports together with supporting research from industry and academia. These are available to organisations that meet the requirements of an access test, which simply asks you a few questions about your organisation, how accessing the data will benefit the UK and zero carbon technology research. Our restricted reports include FlyZero technical reports, reports from offload packages placed with industry, UK manufacturing catapults and academia. The list of reports is too long for me to step through today and covers sustainability, aircraft concepts, commercial strategy, industrial strategy, technical reports and many more. Thank you for attending today, and please make a note of this simple web address for accessing our project outputs. Thank you.
Good afternoon, everyone. My name is Mark Willier, and I have had the pleasure of being the Chief Engineer for Airframe on the FlyZero programme for the last 15 months. I just wanted to take 5 minutes to give a personal reflection on the leadership of the FlyZero programme. I'll touch briefly on the challenges and the learnings we found. So, what were the challenges? When we started, not least, there was the backdrop of the pandemic. The country was in its 3rd lockdown and all of our early engagements were conducted remotely. It's hard enough at times to establish trust and respect with a new team. It's incredibly difficult if you're trying to do this remotely. We had a really stiff ramp-up challenge. We needed good people and we needed them quickly. And in many instances, the skill sets required were in specialist areas that were already in high demand. This is enough of a challenge under normal circumstances, an incredibly difficult one if you're trying to execute this remotely. There was also the very broad scope of the project. The grant offer letter from the government set out specifically what was required. There was no firm view at this point, however, as to how that should be delivered. There was also very little familiarity within the leadership team. Few of us knew each other, even fewer of us had the opportunity to work with each other. Whilst we didn't realise at the time, this would also prove to be the case with the yet-to-be recruited team. The model also hadn't been tested. Multiple companies effectively working in a single room in a truly open and collaborative way, driving towards a single purpose. We really didn't know at this point how this would work out. There were little or no project-specific processes. Effectively, the corporate safety blanket had been removed. For some people, this proved challenging. For others, it actually proved empowering. Well, what do we learn? And for me personally, the last 15 months have been an absolutely huge learning experience. It may not be ideal, but you can achieve in a largely remote working environment. But you have to work at it. You really have to work at making it work. And that's not just the leadership team. That is everyone. You have to find a means to establish trust and respect without being in the same room. Does the model work? Under the right circumstances, the model definitely works. It is possible for representatives from differing businesses to work in an open and collaborative way with the same goals. Egos and biases can be left at the door if the purpose is singular and the outcome, at least in my opinion in this instance, was far greater than the sum of the parts. The contributing companies put forward great people, and they're all a credit to their organisations. And for this, we owe them a huge debt of thanks. And that doesn't in any way detract from the FTCs that we were lucky enough to find and recruit. Ultimately, the people you employ are everything. And they all came passionately to support this cause with an open mind, huge capability, and a willingness to engage, learn, and ultimately succeed. The UK aviation sector has huge capability, both in industry and academia. We all have a responsibility to look to protect, nurture, and grow this for the future. The FlyZero leadership team are incredibly proud of what this team has done. And ultimately, at least in my view, the UK aviation sector should be as well. That concludes my presentation. Thank you all for your time, and I genuinely hope you enjoy the rest of the webinar.
Okay.
Yeah.
Hi, James.
Hi, Beth. How are you doing?
I'm good. And hello to everyone joining us virtually. Hope you're enjoying the FlyZero webinar, hearing about all of our findings from the last year. So me and James are just going to have a bit of a chat and talk around sort of James's motivations for joining and reflecting on the last year that we've had. So we'll start by introducing ourselves. So I'll introduce myself first, and then we'll go over to you, James. So I'm Bethany Hall, and I'm seconded to FlyZero from Rolls-Royce, where I'm an electrical systems engineer. And my role on FlyZero has been technical assistant for the project director. And through that, I've got involved in various different things across the project, which included leading our design for sustainability activities, authoring the FlyZero workforce report, and also working in some of the technical teams and the industrial strategy team, looking at our industrial engagement. So yeah, James, introduce yourself, please.
Yeah, so I'm James Coles. I'm seconded in from the consultancy Mott MacDonald, and my role on FlyZero has been as commercial strategy manager. So really defining the commercial requirements for the concepts, the market opportunities, and the market forecasts and sort of market penetration strategies and how can we make zero emissions aircraft competitive and commercially successful in the market.
Amazing, and that's been such an important part of FlyZero, given that we've tried to look really holistically. But yeah, so James, what were your motivations for joining FlyZero?
Well, I think I've spent my career in aviation in one form or another, in a wide variety of roles, and I'm really committed to the aviation industry and to the air transport industry, and also at a personal level, I enjoy travel, I enjoy having holidays and things like that, and I believe very much that the solution to the environmental issues of aviation is not asking people to travel less and asking people to forgo the opportunities to experience other cultures and visit their friends and family and things like that around the world, but to find technical solutions that decarbonize aviation at source. And I think going beyond sustainable aviation fuels and looking at completely new technology that is actually not emitting carbon into the atmosphere is really the right way to go. And I must say, when I joined the project, I was on the skeptical side about how you could make hydrogen aviation work. And I've been really impressed and convinced and become quite a convert to that not only will it solve environmental problems, but it's actually the most efficient way to go forward with aviation into the 21st century.
Yeah, amazing. And my motivations to join were quite similar, actually. I'm a bit of a travelaholic myself, and I had a gap year before starting my grad scheme at Rolls-Royce, and I went to like 12 different countries. I took so many flights, and I'm trying to redeem myself by making aviation sustainable again. Making it sustainable. So how did you find it when you first joined, like coming into the project? We had loads of sprints going. I think you joined about a month or so before me. How did you find joining the project?
Well, it was really quite an amazing experience. They were pulling together a team, which was eventually, I'm not sure what we peaked at. It was sort of 80 or 90 people. When I joined, it was just about a dozen, ramping up to 40 odd people. So I was in that sort of early wave. People coming from all different companies, either as secondees or as sort of direct appointments, but with fantastic experience of the aerospace and aviation industry, and a real mix of people from across the country, and doing all of it virtually in the COVID environment. But I must say, even if it weren't for COVID, we would have had to do it virtually because we're all scattered across the country. So we had to do it in a way that actually suited the project to work remotely. And I think the way it was organized, the way we had some sessions early on, just sort of informal kind of get to know you sessions over Teams, just having a coffee together virtually, so that you could work as a cohesive team with people you'd never met. And actually, most people we didn't get a chance to meet until, what was it, the September time. So it was many months into the project before we actually physically met each other. But it felt like we knew each other for a long time, even though we hadn't most of us hadn't met. So it was a really interesting experience, and I think it was a good example of making a virtue out of a necessity in terms of working remotely in the COVID months.
Yeah, I think absolutely. I don't think we could have been more effective if we weren't mostly remote. because it was so efficient. Like we had daily stand-ups in my team, we had daily stand-ups every day. If we were having to travel to meet up, we wouldn't have been able to keep to the same drumbeat, I don't think. And that conference, it felt like a family reunion, even though half the people I'd never met in person. It was like, it was such a good atmosphere, wasn't it?
It was.
So James, your role was to look at the market analysis. So can you talk a little bit more around the scenarios and which aircraft type could be first to market and how you approached that challenge?
Yeah, so I think the sort of first aspect of that was some upfront market analysis to support the engineers at the very early stage of the project when we were doing the scouts, when we were sort of exploring the design space of what was possible with hydrogen aviation, and that led us to really two things. One was it overturned the scouts overturned the preconception that hydrogen aircraft were necessarily short range. And we found that we could make a narrow body that could fly as far as an A320neo, and most interestingly, from my point of view, the concept of a mid-sized aircraft, of an aircraft that could fly London, Hong Kong non-stop, and then onwards to Auckland or Sydney, that you could get anywhere in the world with a single stop with a hydrogen aircraft without going to some radically new layout like a blended wing body, which has all sorts of issues in terms of airport compatibility and stuff. So it's still a relatively conventional aircraft with hydrogen could fly long haul distances. So that was really interesting revelation that kind of came as a kind of a joint thing between what we could see from the market side and what the engineers were telling us was the art of the possible. And then that fed into our whole approach to our market forecasts in terms of forecasting the total market and the market penetration and the different scenarios. And the key to the scenarios for FlyZero was basically that by far the biggest sector of the aviation market is the narrow body sector, the sort of A320, Boeing 737. It's more a bit over half of the market by value, and roughly half the market in terms of, or half the carbon emissions. So it's clearly the most important market to address, but because it's so big, it's extremely high risk for the manufacturers and the airlines if you were to tackle that sector first with novel technology. So you need to develop the technology and de-risk the technology in a smaller, lower risk market first. And the traditional thinking was you start with a regional aircraft and then you grow to a narrow body and then maybe bigger. But what we discovered as we looked at the market and looked at what was coming out of the scouts was we became more and more attractive with what we called the mid-size first. So starting with this sort of 200 to 280 seater longish haul aircraft, 5,000 plus nautical mile range aircraft, which sits between, say, the A320 and the A350 in the Airbus pantheon. And so it's not competing with a new modern product. It's filling a new niche, but it makes a big difference in terms of carbon emissions because each of these aircraft fly a long distance. So the mid-sized market is about 5% of flights, but about 19% of carbon emissions. So it makes a sizable difference, and also sets the scene for the technology for the narrow body aircraft, and also has upward scope to eat into the longer haul wide body market as you kind of mature the technology and develop it. So it makes a much bigger difference to carbon emissions as a pathway towards decarbonizing aviation altogether. So we became very attractive by this mid-size first strategy, and that's kind of our lead strategy coming with the project.
Amazing. And so what sort of learnings from the approach that you took in FlyZero will you take back into organization and your future roles, do you think that you worked much more closely with the technical teams than you have before, or what kind of learning will you take forward?
Yeah, so one of the real strengths of the FlyZero project was the depth of the aerospace knowledge. People from Airbus and Rolls-Royce and GKN and the other companies. Really fantastic experience that gives real credibility and real substance to what we've come up with. Going back to my job with Mark McDonald on the consultancy side. A lot of our work is more on the airport side and the infrastructure side. So I think a big part of this is understanding how aviation, the different pathways for aviation to decarbonize, and how we can help develop the supporting infrastructure that's absolutely necessary. And I think that was one of the key things of the FlyZero project, that because it was an integrated project of different skills, it's addressing head on the issue that there's no point just developing a hydrogen aircraft all by itself. It has to be done in concert with the rest of the aviation industry, with the airports, with the airlines, working together. Because it's too big a transition to happen in a haphazard way. So it's been tremendous from that point of view, and how we can integrate the learnings from FlyZero into the other things that Mark McDonald does in the sustainability space, in the airport infrastructure space, in the energy space. It's been really important for us to be part of the project and be one of the contributor organizations. Mark McDonald's quite proud to have been part of the project, and for me personally, I started my career many years ago as an aerospace engineer, and then I drifted off into other parts of aviation, and it's been quite nice to sort of come back to this sort of conceptual design and get my teeth into these sort of issues again. So it's been a fantastic sort of personal learning experience as well.
Yeah, that's phenomenal. And I think one of the benefits of FlyZero is we've had people from all across industry and all different stages of their careers. Like, I'm much earlier on in my career, and yes. I'm like, I have so many opportunities, and I have so many ideas, and like I have a great big network now for sort of moving forwards in the sustainable aerospace sector, and making sure that we keep the unity amongst the FlyZero team, and we keep talking, even though we will be going back to our home organisations. But I think everyone's found value.
That's a really important point. We have been quite diverse in terms of where we've come from, but also, as you say, in terms of where we are in our careers. There's some on the team who are this is sort of their last project before they retire, and they're really enjoying it. There's others, more in the middle, and then there's people like yourselves who are more at the beginning of your career. And although we've all been working virtually, I think we've been, sharing that knowledge across the team as well.
Yeah, absolutely. I think that's all we've got time for. But it's been good to chat, and I'll see you soon.
Yeah. Thanks, Beth. See you soon.
Hi, welcome back. So I'd like to say thank you to all of our presenters, and hopefully that's given you a really good sense from the team about the experience of working on FlyZero, some of the challenges, some of the benefits, and how they've managed to overcome really quite a substantial challenge of building this amazing team and running a project through COVID. As you can see, I'm back with some of our presenters from today for our Q&A session. As a reminder, you can ask a question by scanning the QR code or by visiting slido.com and entering the code, which is 547152. There's quite a lot of questions on there already, so I'm going to plug straight in. And we've had a question about academic research. And so, Chris, can I start with you? What more academic research do you believe needs to be done?
Yeah, no, thank you, Sophie. from our research, we can see that we're lacking in some of the skills around liquid hydrogen and the application of liquid hydrogen into products. We really need to develop a lot more materials, especially very low temperature materials, and look at all the structural assessments of those materials, as well as on the climate science, looking at how we can predict the emissions and where they go after they're emitted out the back of an engine, and how do you get zero carbon or net carbon extraction of carbon that you put at atmosphere at 40,000 feet. So a lot of work, and I think the key thing is around skills and capability in the UK and building our knowledge for these new technologies.
Okay, thank you. Naresh, I know you've been particularly looking at the climate science. Is there anything you would add to that?
Climate science is really fundamental. I think certainly we've gained a huge amount of knowledge by working with universities and their capabilities, such as at Leeds University. We've consulted with Imperial College, experts at Reading and Bristol and Cambridge, and I can go on and on and on. These experts are world leading. Some of these people are actually advising the United Nations at the Intergovernmental Panel for Climate Change. So we're very, very privileged that we've been able to harness the input from these folk into the analysis that we've been doing. And one of the strongest recommendations that we've put forward for sustainability is improving those atmospheric and chemistry models that need to be further improved for our use as we go forward. And this is all detailed in the reporting that you've already pointed out to the audience.
Thank you. And Katie, in terms of the areas you were looking at, is there more academic research that needs to be done?
Yeah, so my team's been looking at materials and manufacturing and industrial strategy. We worked with 10 different partners, many of whom are in academia on materials, and there's a great report on the website now about all the materials challenges. There's a fundamental one which is about qualification of materials and understanding how hydrogen interacts with it, and therefore enabling aircraft with the life, I suppose. That needs to be addressed very urgently, and it's a collaborative activity between industry, academia, test houses. But academia are also essential for breakthroughs, future breakthroughs in technologies across the patch. And so there's an opportunity, I think, for increased collaboration between academia and industry through this technological disruption.
Thank you. Naresh, I'm going to come back to you. You were leading the sustainability work, and so in terms of the modelling, can you explain how you have included any environmental impact from hydrogen? And the question specifically asks about potential leaks or venting.
Yeah. Very good question, actually. Hydrogen acts as a greenhouse gas directly. So any leaks or vents would be a significant concern for anybody. Hydrogen is about 5 times more potent than CO2 as a greenhouse gas. So actually preventing and eliminating leaks and managing venting carefully are key things that will need to be handled as we go forward. So let me just point out a couple of things. Firstly, at the aircraft level, I should point out that the team has calculated that the rate at which hydrogen needs to be vented from the tanks is less than the rate at which hydrogen will actually be consumed by the propulsion system. So actually we can manage venting of hydrogen in the aircraft readily. Of course, the technology needs to be developed and effort need to be put into there from an engineering perspective. The second aspect of this, which is probably what the individual who's asked the question is rightly concerned about, is what about leaks, potential leaks from infrastructure and the way you supply hydrogen to the airport and where it's generated and in refueling the aircraft itself. And again, my answer to that would be that requires engineering effort in order to manage those leaks. But certainly some of the detailed work that the engineering team has done on cryogenics, materials, the way in which storage can take place, I think has identified that these are not presenting any barriers to their implementation.
Okay, thank you very much for that. Mark, can I turn to you and ask you about energy production? We've talked a lot about the need to increase production in order to be able to get the amounts of green hydrogen either as the fuel source or to create kind of SAF going forward. Do you think we're going to be able to generate enough electricity to sustain the types of aviation demand that we're assuming?
It's a really good question, Sophie. I mean, essentially, this is a big challenge. Yeah, let's not ignore that. It's a huge challenge, but it's a huge challenge for the UK, for our country, but it's a challenge for any other country as well, because we've got to wean ourselves away from fossil fuels. Yeah. And just to give a stat there, I mean, today, after a whole energy demand, only 20% of our energy sourced is actually renewable. 80% is from fossil fuels. We've got to wean ourselves off that. So if you look at the UK and the UK strategy around hydrogen today, there's a target of 5 gigawatts by 2030, yeah, which is about 45 terawatt hours. Similarly, you see similar strategies elsewhere across Europe, Japan, etc. So strategies are in place to generate hydrogen. We took a look at the national grid's future energy scenarios as well. So they've taken a view of what does 2050 look like, and what is the size of that transition, and that's really interesting in the moving from that 20% of renewables to potentially something like 90% of renewables by 2050 is an enormous challenge. Yeah. But we can't necessarily take that on aviation's shoulders. That actually is a national priority ultimately. So we've got to. Aviation is a strong use case in here. Now, the interesting thing for the future energy scenarios that National Grid took on board is that they had identified about 75 terawatt hours per annum for aviation and maritime combined. And our analysis suggests that if you had a strong penetration of hydrogen aircraft, it would be more than that. It'd be 90, 100 terawatt hours, but it's of the same ballpark in reality. Okay. So I think we've got to take some encouragement that those views, that requirement is being accounted for, and ultimately, we can't afford to carry on living with fossil fuels.
Yeah. Okay, thanks, Mark. And I think it's really interesting the way that you described that. It is a global and a national issue, not just an aviation issue. And I think that's absolutely right. And there are a number of areas, aren't there, within the FlyZero project where we have seen that you've been pulling together potential challenges, but actually they're not just aviation challenges. They kind of go across. And maybe actually we could stay with you and perhaps bring Katie in to talk about the global challenge. Do you see a need for global legislation in this area in order to be able to advance in a more sustainable way in aviation?
If I start, Katie, then over to you. Absolutely. I mean, this is a coordination failure potentially.
if we don't actually line all the actors up across the energy sector, aviation, aerospace, we've got to have, and therefore the legislation that goes all with that, we're going to fail. The encouraging bit is from COP26, 23 nations all signing some commitments to actually decarbonize. We've got to play off the back of that commitment, and I think it's that kind of commitment and more countries signing up to decarbonisation. That's the thing that's going to actually really deliver this. Katie, I'm sure you've got some other things to add. Katie, you're
Katie,
muted.
we seem to have lost your sound.
Sorry. I think my preoccupation is all about how we get global aerospace companies who are either multinationals or even the incomers tend to have sites in multiple nations or be footloose, so able to move about between nations. How do we get all of those working together, across kind of the constraints that we have, so the trade agreements, in order to develop these technologies together and bring the full global force, I suppose, the engineering force to bear upon this problem, and the solutions for that I think we're really keen to hear about and to collaborate on in the UK.
And I think, as you've mentioned, COP26 brought together a number of countries with the same aspirations. Actually, heading forward into ICAO this year will be another really good opportunity to take a step forward. And it feels like internationally we really need to build some momentum. And I know, Katie, you spoke to a number of countries about what they were doing in this area and about the findings of FlyZero. I don't know whether you've got any kind of comments on how they are progressing in a similar way, or indeed what more we could do with them.
Well, Europe's obviously progressing apace, with Airbus Zero E program happening, with clean aviation being very focused on hydrogen. So they're moving forward very rapidly. The USA is moving slower, but they have a lot of capability on hydrogen, and if they choose to move, I think we'll see it happening quite quickly. And they have had a lot of experience in a lot of projects on hydrogen aerospace projects in the past, and are beginning to announce reviews into this technology area as well. But what's interesting is seeing the Far East moving, so Japan and South Korea. They're really assertively building capability in hydrogen aerospace technologies, and I think that's a real opportunity for collaboration for us, as well as with our European and US partners.
Okay, thanks, Katie. I'm just going to move slightly on to talking about hydrogen specifically. Simon, can you talk to me about what safety concerns do you think are going to be the hardest to mitigate in this area?
Yes, thanks. So we are aware that the use of hydrogen as a fuel presents some differences in the behaviour of the fuel, the way the fuel is stored, and there's some challenges around that. We've been thinking about how we could deal with these. We've been working directly with the Civil Aviation Authority and the Health and Safety Executive, who have some experience in these areas. We've been discussing how we might address some of these concerns going forward. We've also thought about the overall layout and the design configuration of the aircraft, and we've made some early macro design decisions around the configuration. For example, we've moved the cryogenic tanks, the fuel tanks, out of rotor burst arcs to avoid a potential rotor burst being able to pierce tanks. And we've thought about the potential failure arcs of wheel and tyre bursts as well. We've then thought about some of the topics of consideration. So things like hydrogen refueling. What technology may be required? What experience do we need to draw upon to make sure that refueling could not only be done rapidly but safely? How would you seal at the point of refueling when you're taking the nozzle out as well? What would the keep out radius need to be based on today's experience, drawing on the space industry? But what testing would need to be done to drop that in the future to allow simultaneous activity, as Chris talked about before. We've also thought around the difference in challenge of leakage of hydrogen around the tank, around the fuel system. What might we need to do to mitigate that, to ensure sealing? And if there was leakage, would we need to vent around the hydrogen fuel system, for example? Also, with the new technology being introduced, new units, new equipment, we've thought about what that might mean from a reliability point of view going forward, to make sure you always have a reliable delivery of the fuel into the engine or fuel cell around the envelope of operation. So these are the types of topics we've begun to get into, and we've started a conversation with the CAA. They're by no means finished, complete, those. There's a lot of work we need to do going forward, including testing of the assumptions we've made. Going forward, if there's an infrastructure investment, having real hydrogen unit testing going forward to back up some of the challenges we've put out there.
Thank you, and that links obviously to the conversation we were having earlier, where you talked about testing. And Mark, if I kind of move on from that, then so what do you think the route to certification of hydrogen is?
Thanks, Sophie. Yeah, and some of this really follows on from what Simon's just laid out, that we have, and it's very much the start of a journey. We have engaged with the CAA. We were fortunate also enough to have a CAA panel member who sat on our design advisory group, and that was really useful and helpful for us. And there's definitely a way to go, and there are some big challenges with the route to certification. And a lot of the stuff that we've talked about and we've laid out in our safety and cert report will also talk about the fact that it will become a global solution. It won't be individual countries, individual certifying authorities that will dominate this. It will have to be a collaboration, and that collaboration will be internationally, as some of the other guys have already spoken about, and also between industry and the certifying authorities, because effectively the certifying authorities will not be able to draw down on the huge industrial experience that they've done with traditional aircraft for the last 70 years. This is a new problem, and if it's to be resolved quickly, our view is there need to be stronger collaboration between industry participants and the certifying authorities.
Thank you.
Sophie,
Yes, of
Sorry,
course, Chris.
Sophie. I was just going to add to the conversation, because I'm really interested in the fact, we're talking a lot about hydrogen and venting and the management of it. And if you go back to what I was saying earlier, one of the things that we do recognize in FlyZero is we've looked at these topics, we've studied them, we've come up with some views and recommendations, but we haven't able to close out every action. So when we talk about things like venting and the way the hydrogen might act, some of that is still new research areas that can be looked into, but also there's a huge amount of engineering that can go on to maybe eliminate them, in the future. So the reason we talk about venting is because we see when people are using hydrogen on rockets, they vent it. Doesn't mean you have to on planes. And so to me, there's an open question. Do you actually need to vent, as an example? So I think there's still lots of challenges, and that's one of the huge sort of disruptions of the hydrogen that we need to all look at and work on. Thanks, Sophie.
Yeah. No worries, Chris. I think that's a really good point. I mean, this study has produced an enormous amount in a very short space of time, but it's clearly not completely comprehensive, and it's only as good as what you can do on paper at the moment. So, there is a huge amount of work that needs to be done further to validate some of this. There's some interesting questions coming through on Slido around industrial capability and asking essentially how you've engaged airframers in this discussion, but also going forward, could we develop a UK whole aircraft capability rather than relying on some of the current OEMs? So, Chris, can I ask you to comment on that first, and then I'll come to Katie?
Yeah, I mean, we have studied this. I mean, the investment needed for a whole aircraft capability is humongous, and we're talking 15 billion to maybe 30 billion, depending on what size of aircraft and the complexity. And this is all new. So the big issue for us when we look at this is, how do you find that sort of funding mechanism, but also how do you find the experience of certifying a whole aircraft? And our view became one of, we don't believe the UK's got that capability anymore to build a large commercial aircraft and deliver it on its own. And the global aviation community shows you that this is a global, national, not national, but international type approach. And therefore, actually what we need to do, and this is the real challenge for us all, is we need to link up the global aviation community and aerospace industries and each take a piece of the work to develop a final solution. And I think that is the right approach to take, which is why you'll see in our reports we talk about technology bricks, because we recognize those are really important bricks. They relate to our knowledge and capability in the UK, and you can actually then use them to make and help the UK grow and be part of the leadership team that develops the next generation of aircraft.
Thank you. And Katie, you were involved in looking at some of these technology bricks and the capability that already exists. Where would you suggest that companies are focusing and looking in order to progress towards some of the timelines we talked about earlier?
Well, in the UK, we've got to fill the gap in cryogenics capability, I think, in order to address this challenge. So however we do that, we could import, I suppose, knowledge, so encourage companies to locate here, import skills, or create more programs that are around rapidly building cryogenic capability. One of the great things about FlyZero is that it's kind of acted as a skills sandpit, and a lot of the engineers on the program have learned about hydrogen, how to deal with cold. We need to expand that so we've got enough of a critical mass in the UK. So companies who are in other sectors in the UK working on cryogenics, you should be reaching out to aerospace companies at the moment, because several of them are moving. We've got projects live with people like GKN Aerospace, Airbus are obviously moving through their Zero-E program. And so creating those connections at this point in time is really key to accelerate activity.
Thanks, Katie. And I think, just harking back to what Simon said earlier, there's not only opportunity to come into the aerospace industry, but then potentially to be able to exploit that into other sectors going forwards as well. So it's quite an exciting time. Now, I don't want to end on a downer, but I'm going to ask the question because it's been asked. Are we being too positive about hydrogen? There are a lot of challenges to move forward from where we are today to where we need to get to. So I think as a final question, I'm going to ask you all essentially for your reflections, given that you have looked at such different areas. So Chris, if I start with you, where do you see the challenges and how do you view the opportunity?
To me, the challenge is going to be in delivering the engineering solutions, but also manufacturing at rate the materials, i.e. the fuels and that for these aircraft, and then connecting it globally. But I think the real thing to remember is, why are we doing this? And that's because we want to protect our planet and we want to make sure that we can control climate control. So we're not doing this because we want to do it and think, I think this is important from a green planet point of view. So always remember that.
Thank you. Mark Willier.
Yeah, I guess similar to Chris, and his response was comprehensive. This is about weighing challenge versus necessity, and change is becoming a necessity, as Chris said, in order to protect the planet. And I think that pretty much, for me, Sophie, sums it up.
Okay. Katie, in terms of the challenges in the industrial strategy sector, you talked about the need for companies potentially to come in. Do you see other challenges facing UK companies in this area?
Yeah, I think so. Some of the competencies we're going to need don't exist in the aerospace sector, and so they're going to have to come from outside the aerospace sector in. And obviously there's very high barriers, not just to certifying an aircraft, but to even operating in aerospace. And so I do think there's space for partnerships, risk-sharing partnerships between existing aerospace companies and those outside the sector, but also for help for companies who are trying to enter into aerospace through this technological disruption to understand the quality systems that are really critical to the safety levels, that those manufacturing and prototyping, quality control. So we absolutely have to kind of attack that head on and not make it a barrier to innovation.
Okay. Naresh, you talked earlier about the need for more work into climate science. Across your portfolio, where else do you think there really needs to be a focus?
Well, having listened to my colleagues over the last 15 months, the conclusion I've come to is that hydrogen is technically feasible, it's commercially viable, and it's environmentally sustainable. I think in answer to your question, I think there's a lot of work that needs to be done, which I term as verification and validation. I think both to confirm our really, really strong findings. And as the program director has rightly pointed out, there are still questions that have a degree of uncertainty. And I think it's right for us to urgently look at those areas of uncertainty. And certainly climate science is one such area, which I will be pushing hard as we go forward.
Thank you. And Simon, there's a huge amount of work ongoing at the moment in the area of propulsion and new fuels. Is there anything you'd like to add in terms of the challenges that we've got?
Yes, I think that there's a lot of work going on, and there's some big challenges to be addressed in propulsion. I would just open back out to the original question on where are the really big challenges across this whole system. I think halfway through this program, my perception was there was a huge challenge to synchronize effort in fuel production, in the ground-based infrastructure in airports, and in the onboard technology. I think with what we've shown in FlyZero, if you can go with a mid-sized concept and a narrow body and you can address regional as well, that helps address the chicken and egg problem of who needs to move first, because we've shown you can address the vast majority of the market. And in doing so, we increase the attractiveness of all three of those. So I think we've shown that there's a real way forward and an attractive market to invest in all three of those elements.
Okay, thank you. And Mark, I'm going to give you the final word on this.
I'll be quick because I saw the wrap-up prompt as well. The guys have said it all already to an extent, but I think the final word is going to be that people still want to fly. The social benefits of flying, promotes peace around the world, promotes people meeting, understanding cultures, and we owe it. We have a moral obligation to keep people flying, but we can't do it at any cost. And just as Chris said, we have to do it in a sustainable way. And I think our collective view is that liquid hydrogen is the right propulsion system, or is the right propulsion fluid to actually achieve that goal.
Thank you. And I'd like to thank all of you for taking part in this panel and for all of the work that's gone into the last 15 months. An extraordinary amount of outputs, some real high quality information available for everyone. And please do check into the website and get hold of that. I'm now going to hand over. We've got a very short video on the FlyZero experience, and then I'm handing over to Gary Elliott for some final comments. He's the CEO of the ATI, and he will be looking at kind of where we go from here. So this is goodbye from me. Thank you very much for your time.
FlyZero is a very exciting project. Since I joined, I get an opportunity to meet up quite a lot of specialists from various industries and draw down their experiences and take away something from that for the benefit of my own learning and development.
The most I enjoyed about FlyZero so far is teamwork. Meeting new people, working with experts along different domains and learning from each other. That's definitely something to enjoy. So one of the things that I will be taking back to my parent company is definitely the knowledge about sustainable operations, how to embed them in the daily life and how to make sure that the aviation becomes greener than it is today.
What I've enjoyed really is the immense sort of talent we've got within FlyZero. Really, every day has been brilliant. Just having conversations with really intelligent people and discussing ideas and options on technology and technology development. That's been extremely exciting.
In FlyZero, I've learned about all the different technologies that it takes to make zero carbon aircraft, but I've also learned that it's not just about the technology solution, it's about the sustainability assessments, it's about the commercial viability assessments, and it's also about the industrialization.
It's super exciting, the future of aerospace, just because I can see that sustainable air travel is coming.
Well, hello everyone. Thank you for joining us today. It's over to me to close today's webinar, and I'll just say a few words if you don't mind. So firstly, I'd like to thank BAYS, our contributing companies, research partners, the FlyZero team and the ATI team for all of their hard work. They really have demonstrated what can be done during these challenging times, pretty much remotely all the way through. So as you've heard today, the project is very much focused on zero carbon emission flight. And the reason I was eager to have the project was to get an informed view of the most likely technologies that will succeed in our ambitions to reach net zero 2050. And as outlined by the team today, they really have made some tangible conclusions, and I'll outline in a moment what we will do with them next. Before I do that, I just wanted to highlight the fact that there are many other technologies and solutions required for net zero aviation, and all of these are equally important. And these will be outlined in the ATI's broader aerospace technology strategy, which we will release next month. So the transition plan from FlyZero into core ATI is underway, and following the end of the project, the ATI will do the following. So I'll just outline a number of key points, please. So first, we'll incorporate the key findings from FlyZero into the ATI's technology and portfolio strategy and seek to maximize the outputs and conclusions where feasible for the UK. Secondly, we'll continue dialogue with potential industrial partners about opportunities for collaborative research and development projects in the UK. Next, we'll work with our academic partners to review opportunities for research within the universities on the back of the conclusions. We'll enhance the ATI's capability and resources to secure UK capability. And lastly, we will utilize the findings as part of the expanded ATI advisory network to further challenge the conclusions and opportunities for the UK in its net zero 2050 target. So lastly, well done to all of those who have been involved, and many thanks for those of you who have taken the time to join us today. I hope to see many of you at this year's Farnborough Air Show. As always, the ATI will have a stand, so please come visit and join us. So thank you and goodbye.